going. Keep going. Fine. We must be near the island. I'll get you there.
presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream here today for our live lecture. So, if you don't know who I am, my name is Dr. Daniel Page, but you could just call me Dan or Daniel. I'm that guy that's on the screen at the moment. But anyways, I hope you're having a beautiful day so far and you're staying warm. A couple quick things before we get started. The first thing, if you haven't yet, make sure to subscribe or follow for where you're watching this. Of course, you can check out and hang out in the live chat, for which I take questions. If you have any fun things to say, please hang on out. We have ourselves a great time over here. And in addition to this, if you want to support this work beyond just sharing the video or liking it, please tell your friends to come hang out. And of course, check out my Patreon, patreon.com/PageWizard. I have all sorts of rewards over there. But enough of that. Let's get started, okay? So let me just see if there's anything going on. No, let's just get into things here. So if you're enjoying the stream, please let me know in the chat. And of course, if you have any questions, please don't hesitate to ask. So as per usual, if the live chat is on the screen, it will be audible on the stream. And keep in mind, I can see the stream. It's right there. And also I can hear it. So just please keep that in mind. So just because you can't see the chat on the screen doesn't mean I can't see or hear it, okay? It's not like a phantom or something. So, anyways, today we're going to be talking about another type of, because in previous lectures, we've seen different types of counting arguments, particularly the types of what we call combinatorial arguments. So, namely, you want to know, hey, look, I have this many things versus this many things. Is there something I could say about this set of things versus that set of things? And normally what we do is we try to pair them up in some way. Or that's example one way of doing it. But generally the idea is that I have one set of things, another set of things. I would like to be able to say one thing about this thing versus that thing. And I try to make some correspondence or say that they aren't in correspondence with each other. Meaning I can't match them up. So there's a lot of different types of arguments like those. Previous lessons we've seen, for example, like the handshaking lemma, which will come up some point later on in today's lecture. That employs something called double counting. That's where, for which when we do our counting, we end up doing twice as many counts than there actually are of objects. But the trick is that by double counting, we're counting for generally all of the counts of the objects, but we're making sure that we're not leaving any out. But by double counting, we have an exact count of how many we're over counting. But we've seen a bunch of other ways too. We're going to see one namely here today. In fact, we're going to see two. We're going to be seeing the pigeonhole principle, and we're also going to be seeing something called the averaging principle, which is its lesser known cousin. So we're going to see the relationship between these two principles. We're also going to see some examples for which how we apply them. And Miss Kitty is here. Everybody make sure to say hi to Miss Kitty. But anyways, that brings me to today's first part. So we're going to start by talking about the pigeonhole principle here today. So first, one thing I want to bring up is that we have all sorts of cats. You know, I got Miss Kitty here. Hello, Miss Kitty. And they love boxes. They love boxes. Miss Kitty loves boxes. Mochi the cat loves boxes. The point is they love getting in boxes. And they aren't the only cats that do. I have a whole crew over here. I got even Pusheen over here. They love getting in the boxes. So, for example, here I got a box here. Here's a box. Miss Kitty, you're gonna get in this box, okay? You want to get in the box? Here, come on, Miss Kitty. I know you love getting in boxes. Come here. There we go. So Miss Kitty went in the box. She likes being in this box. She's just ready, excited in here. So that also includes other cats, like Mochi the cat too. I don't know where Mochi is. Mochi might be having a nap. She might be staring at me somewhere randomly. I'm not quite sure. She She has a tendency of staring at me like some sort of automaton. I don't quite know, but the point is that she's somewhere. But either way, we need Miss Kitty here for our helping us here. So when we put Miss Kitty in the box, now Miss Kitty, are you enjoying yourself in there? Yeah, she's enjoying herself. So keep in mind that when we have a box, this is a discrete object. Likewise, Miss Kitty is a discrete object too. Now, obviously, she's more than just an object, right? She's a lovely, lovely kitty, right? Now, I would like to know something about how many kitties can be in a box. Keep in mind, if I had Mochi the cat, or say Pusheen can go in the box with Miss Kitty. And now there's 2 kitties in the box, right? Now, I could have another kitty. Let's say here's this kitty. I could put this kitty in this box as well. So now I have 3 kitties in the box. See? Right, Miss Kitty? Meow. So we could have 3 kitties in the box, and so on. Now, what if I were... Now, this isn't terribly interesting in its own regard. Yeah, I know, Miss Kitty. I know. This is your box. I know. But what if I had more boxes? Say if I have 2 boxes. Suppose I have 2 boxes instead of just 1 box. And say cats are going to be going in these boxes. Say Pusheen decides to go in this box instead. So when I look at these, and I can keep in mind, I can keep track of how many cats are in each box, whether I want to choose to examine them one by one, or, yeah, I know Pusheen's in there. Are you a little jealous? So there can be a cat in each box. There may be a cat that's not even in a box. It may be in another box. I would like to be able to say something about if I have a certain number of boxes or bins versus how many objects, say cats, how many cats do I have in a box? So see, Miss Kitty's decided she wants to go check out something else. But the point is, imagine that I have all of my cats and I'm going to allow them to get into each a box. They don't have to necessarily get in the same box. They may not necessarily even get in different, all distinct boxes. But I would like to be able to tell you something about how many cats are in some box, at least. So that brings us to the pigeonhole principle. So let's talk about this now. So what if there are more cats than boxes? And you don't have to think about just cats and boxes. We could just think of these as all sorts of things. Like these could just be objects. These could be socks, for example. And this is some bin that you could put the objects in. Just like our cats go in the boxes. So what I want to see is there anything we can say about if there were more cats than boxes? Is there anything I can guarantee about the number of cats or objects in some box or respectively bin? So that brings me to talking about the pigeonhole principle. So is there anything we can say about the number of cats or objects in some box? Now, note I just said some box. Like for right now, there are 2 boxes. Sorry, 2 boxes here, right? This one has no cats in it, but that one has 2 cats in it, right? It has Pusheen and it got Miss Kitty in here. So suppose that those are all the cats I have. I have 2 bins here. Notice that I don't have more cats than there are boxes, right? So maybe if I brought in a 3rd cat, maybe I might be able to say a bit more. Hey, come here, Mochi. Mochi, come here. Come here. So say if we had a 3rd cat, say Mochi here. Mochi wants to go in the box. So we have 3 cats. Miss Kitty, get back here. Come back here. Come back here. So suppose I have 3 cats. Oh, there goes Moch. Okay, suppose that I had a third cat, say this one right here, and we put this one in this box. What can you say about the boxes? Well, notice that I have more cats than boxes, so most certainly there's something that's interesting that's going to happen here if I have more cats than boxes. So the point I'm getting at is we're going to have ourselves some fun with some boxes and some cats, or respectively, some objects and some bins. So let's characterize the pigeonhole principle. I'm having some destruction derby on over here. The cats are like boxes everywhere. Let's get this box back up here, because otherwise the cats are going to go bonkers. Let's put this box back up here. The cats will go too bonkers if we keep all the boxes on the floor. Sorry, I'm getting really excited about this. I just got cats everywhere, okay? This is the secret of today. So anyways, just to summarize where we're at. I have cats and I have boxes. Like Miss Kitty and maybe Pusheen and maybe Mochi. And they love getting in boxes. Suppose I have some cats and they all decide to go in some box. Now I don't know where the cats went to go into their boxes, but I would like to be able to tell you something about how many cats are in some box. So if I assume there's more cats than boxes, or respectively more objects than there are bins, so these objects are placed in the bins, what can I say? And this brings me to the pigeonhole principle. So we're going to try proving this together. So this is what we call the pigeonhole principle. Pigeonhole principle, it works like this. So now suppose that we're given a positive integer n. So it's just the set of all integers, but only the positive ones. So I'm saying n is one of those. Suppose there are at least n objects. So that means n or more, like say n plus 1. And m bins. Where the number of objects is strictly more than the number of bins. Right? So what is that? So that just means that n will be something like, if the number of bins was m, I'm saying that the number of objects is at least m plus 1, or respectively, I'm saying that n is, say, the number of bins is like n minus 1 or less. So what am I saying here is that if we have this setup, where n is strictly bigger than m, where n is the number of objects and m is the number of bins, then there is a bin with at least 2 objects. In particular, you could say two objects, at least 2 objects. It's 2 or more. So what does this mean in the context of our kitties? That means that if I had 3 cats, for example, and 2 boxes, that means that at least one of the boxes has 2 cats in it. Just as an example. But we're going to prove this claim, and arguably I'm going to tell you that this is a really cute argument. And here's the game plan. Now, suppose that we didn't have this property in play. Suppose otherwise. So we're going to try to come up with what we call a contradiction. So if we're supposing these conditions, and if it's the case that there's a bin with at least 2 objects, suppose that isn't the case. Suppose that's not true. So assume otherwise. What does it mean then? What does it mean for it to be that there is no bin with at least 2 objects? What does that mean? what does it mean for there to be a bin with no, that can't have at least 2 objects? So what is the opposite of that? So, what's the opposite of at least 2? So I'm not saying at most 2, I'm saying at most 1, right? It's going to be that each bin has to have no cats in it or no objects, or it has 1 cat in it or 1 object, respectively, right? Because if otherwise, then there's some bin with at least 2 objects or 2 cats. So this is how we're going to lay out the argument. We're going to use contradiction. So we're going to see what happens when we set it up like this. So assume otherwise. So assume otherwise. If all the objects are placed into bins, then, as we just discussed, then it follows that every bin contains at most 1 object. Right, that's the game plan we have, right? That's what we've set out so far. So, let's think about that. Suppose that This kitty's pushing a box on the floor. It's just, I'm losing it over here. Anyways. So now, think about this. Think about this very carefully. If every bin contains at most 1 object, if that is the case, how many objects can be in bins? Then the total number of objects, and to be clear, I'm talking about the ones in the bins, right? Total number of objects is at most what? Well, there's at most 1 per bin, right? So it's going to be at most, and I have how many bins? Well, I have M of them, but notice that each one has an object in it, and M is strictly bigger than M, right? So it means that how many are in the bins? N. There's at most N. 1 per bin, right? At most N. Most, the number is at most N, right? But what does that mean? But why is this a problem? Well, this by our assumption, it has to also be that this is the number of bins, right? Because we have at most 1 per bin, right? The number of bins, question mark? Well, this doesn't make a whole lot of sense, right? Because how many bins do I got? So, simultaneously, I have it where there is M bins, but M is strictly less than N, right? But that means that the total number of objects is at most what? It's actually this. It's 1 per bin. It's 1 per bin, right? At most. But that's M. But this is less than N. But what does that mean then? There's not enough objects to go into the bins to actually characterize the number of objects there are, right? So that's a contradiction. So what does that mean then? Because remember, the total number of objects is going to be at least what? Well, it's n, right? But we've already established that if I assume this, then I'm not going to have enough spots for all of my objects, right? And this is why we reach the contradiction here. It's a pretty cute argument, right? The strategy we had was we assumed otherwise, then that means that each bin has at most one object. We count up how many objects at most could be in all of the bins, and we realized that there's not enough space in the bins to collect up all the objects. Hence our contradiction here. So this is one way we can prove the pigeonhole principle. Now, let me give you a little bit of background on the pigeonhole principle. So let's just talk a little bit briefly about that. And also I want to mention a couple limitations that the pigeonhole principle has, just because this is a really neat statement. It says that if there's more objects than bins, then there's going to be at least there is going to be some bin with at least 2 or more objects in it, right? So this sounds like a really nice statement, but I'm going to tell you that there's some limitations to it. But first, let's talk briefly about some background. So you might say, Dan, where did this pigeonhole principle exactly come from? Now, it's a nice elementary counting idea. A lot of arguments from combinatorics might use something like this. Sometimes in computer science, you'll find that sometimes people find clever ways of using this pigeonhole principle. And I'm talking from anything from talk about graph algorithms to all the way to thinking about theory of computation. There's a lot of places where this might arise. Because namely, we're talking about discrete objects. So, I must stress that, just some background. Is that it arose at least the 1600s. I have a source in my notes for this fact right here. In fact, there's some documents back from the 1600s where people gave in some examples that include they're of the same spirit of even some of the examples that I will be showing you here today. They're of a very similar nature, some of the examples we'll be talking about here today. So, I'll have a source for this in the notes. But who popularized or is often attributed for the pigeonhole principle is a German mathematician called, let me just write it down, just so you don't look at me cross-eyed. So this is the mathematician Dirichlet. Depending on how you want to pronounce his name, I'll pronounce it as Dirichlet or Dirichlet. In the 19th century, this mathematician popularized this technique. Namely, and keep in mind, this isn't the first mathematician to use the pigeonhole principle, but he had popularized the name, like not the name, but the usage of it. Namely, this pigeonhole principle is also called Dirichlet's box principle. Because just like we were talking about with our cats, you can imagine I have objects that go into bins just like I have objects that could go into a box, say letters, for example. And you may know the phrase pigeonhole, to pigeonhole. We're talking about something as in we're trying to force something into one of the one of the containers. So this Dirichlet's box principle is another way of phrasing this. And if you're wondering more about Dirichlet here, Dirichlet popularized and used this pigeonhole principle to prove some pretty neat theorems in number theory. So that's just a little bit of background on the pigeonhole principle as a common counting argument. So a couple things I want to point out for you. So I must stress that the use of the phrase pigeonhole principle from my understanding, came later though. So the name pigeonhole principle wasn't popularized. It wasn't exactly called that by Dirichlet. It was a German word that basically mounted to about Dirichlet's box or drawer principle. So just some fun background. So often this is attributed to Dirichlet. At least formally. That's what I mean. It's often attributed formally for this. Dirichlet, as a mathematician, developed all sorts of neat things. For example, he was one of the mathematicians that formalized what the modern convention of what a function is. So the formal definition of a function, Dirichlet was one of the mathematicians who contributed to kind of what we call a function in today's terms. Just one of the stepping stones in that process. So often, Dirichlet is often attributed formally for introducing or popularizing the pigeonhole principle. So normally mathematicians will attribute it to Dirichlet. So hopefully you find that kind of interesting. Another thing I want to point out is some limitations, because the pigeonhole principle is an example of something that is non-constructive. It's a non-constructive property here. And the reason why I bring this up is because in computer science especially, you'll find that a lot of theorems tend to be constructive. For example, if I give you the proof of correctness of an algorithm, very often does the proof actually tell you how to build an answer? Not always, but most certainly almost always it does. So I must stress that even though this is a neat combinatorial argument and everything, it has some limitations. It's non-constructive, meaning it doesn't actually provide you an example of the thing for which there is, say, a bin with some object that has, some bin, I'm getting really excited here. It does not show you, for example, an example of where the bin would be that has at least two objects in it. So it's not constructive. It doesn't actually tell you an example. So what I'm saying is it does not tell you things like, one, the bin with at least two objects. It can't tell you that. That's not what the pigeonhole principle says. It just says that there's some bin that has this, right? The second thing you need to be aware of is it doesn't actually tell you a lower bound on how many objects could be in any bin. It just says that some bin has at least two objects in it. It doesn't say that all the bins have at least two objects in it. So it does not tell you a lower bound for the number of bins. Sorry, not the number of bins, the number of objects, right? Number of objects in an arbitrary bin. So I'm getting really excited here. An arbitrary bin. It just says that remember, the pigeonhole principle says there's some bin with at least two objects. Like we talked about earlier, there could be a bin or a box, like we talked about, that doesn't have any cats in it, right? That's possible. They all could be in one of the boxes, right? They could all just be in one. Like, so for example, if I have my friend here, say if I only am considering, say these two cats, I got Pusheen and this cat. Suppose I only have, let's throw in another kitty. Let's get more kitties in here. Let's get this kitty here as well. Suppose I have 3 kitties and I have 2 boxes. What I could potentially have is that all the cats go into this one box. So I have 3 in one box, none in one box. So the pigeonhole principle only says that one of these boxes has at least 2 cats in it. That's all you could say here. Because this box has no cats in it. But this one has all 3 of them. So these are some important limitations I want to provide for you about this. But also, I want to tell you a little bit more about the pigeonhole principle and really what kind of the underlying, I don't want to bring up the dreaded M word, the mayonnaise, where exactly, this concept, why would you, what, is there some formal way of talking about this other than objects and bins? And there's another kind of mathematical object for which we can describe the pigeonhole principle with. It's something we call a function. So, believe it or not, you can formally state the pigeonhole principle as well in terms of a function. So just as a reminder, a function, just like when we talked about our cats, each cat gets put in a box. Each one of these cats loves going in a box. So you can imagine that I could have a function that tells you, hey, look, this cat's going to go in this box. So each cat I give you, it assigns a box for that cat. So in the same way, you can think about this like a function too. So you imagine I give you some object in one finite set. So this is some finite set. And there's some function, we call it f, for example. It doesn't have to be called f, it could be called kazoo, for example. Doesn't matter really what its name is, as long as it's clear. And it outputs, in this case, some other element. And what it does is it sends it so it takes A and sends it to B. So, and that's some element of another finite set. So this is going to be the setup for how we would use the pigeonhole principle if we want to describe it in terms of functions. So just to make this a little easier for us to see, you can imagine this as the set A is your cats, and set B are the boxes. So now really, if you actually think about this carefully, the pigeonhole principle is actually a statement about a function. So all we're doing is we're saying, okay, I have cats, for example. Each one will get assigned to some box. Just like you could think about this in all sorts of different ways. You could talk about all sorts of different kinds of objects. Each one belongs to this collection. You could think of it as a collection or a set. It's easy enough to just work with either one. So I have each one of them, and each one's associated with an element on the other set. So let's talk a little bit about functions now, so that we can talk a little bit more about this in terms of what the pigeonhole principle actually is saying when we talk about functions. Because functions is a much more broader classification than just talk about cats and boxes, right? And likewise, we could talk about objects and bins. Objects and bins are just a way of me talking about a function like this, right? It's just objects and bins are fairly intuitive for us, those that are minds of packing things and other things, like socks in a laundry basket. Or some number of laundry baskets. Maybe you're trying to sort your socks. So let's talk a little bit about functions, just so that we have an idea what we're talking about here. So, let's see what's going on here. So, I want to define three different kinds of functions. Now, I must stress that not all functions have to be one of these three types, as I'm going to show you. But I'm going to define the setup that we have over here. So, we're going to talk about finite sets. Like I have A and B over here. Now, in a function, it doesn't have to be this way, just to be very clear. We work with functions all the time that don't have it where the two sets that I've just talked about are finite. But for our discussion here, we're going to keep them just finite. So given two finite sets. So this is going to be more of a localized definition over finite sets. A and B. So we're going to have finite sets A and B. For some function, and as we talked about over there with our machine, it's going to take each element in A, so each one of our objects, for example, and it's going to send it to a bin. Likewise, if we think of each one of these as a cat, it's going to map or send it, so people would say it maps to this other set B. So there are there are different types of functions. Different types of functions. So we're going to talk about 3 different types of functions here. I'll give some examples. That way you can see, just visualize it a little easier. So don't worry. So here's one, is what we call an injective function. So an injective function, which is sometimes called a one-to-one function. You're going to see why it might be called a one-to-one function. I'll usually refer to it in this discussion as an injective function. So what does this mean? If I give you any 2 elements, so if I pluck off 2 elements from A, for every x and y in A, it has to be that when I pump it through my machine, or in our case, we talk about putting that object into a bin, it has, if we want to use this analogy, I must stress that it doesn't have to work like that. Keep in mind, we're talking about functions more broadly now. What it should be is that the output, this is what we would call f of x, or f of y, if we talk about the other value. It has to be that these two, the outputs of that machine or function, have to be that they're not equal to each other if x is not equal to y. So if they're 2 different elements, meaning that x and y are not the same element, it has to be that when they come out, they don't map to the same element in B. So what do I mean by this? Let me draw you a picture. Miss Kitty, are you being helpful or are you being destructive? Let me draw you a picture just to give you an idea what we're talking about. So just in the same spirit as talking about us putting cats in bins, you can imagine I have set A here and set B. Now suppose that I have 1, 2, 3, 4. I have 4 objects and I'm going to have 5 bins. And each one of these objects is going to be placed in some bin. Do you notice that this is a function because each one of these is exactly mapped to one element in B? But it's actually injective because notice that if I look at any 2 elements in A, they never are going to land and map to the same element in B, right? So does all of them, each one of these, this guarantees that if it's injective, that means that every time I put in input to the machine, it gives me a different element than if any other one of these inputs. So we call it one-to-one. So whenever I put one in, I get another one. But the thing is, it has to be that if they are not equal to each other, meaning that, so if I give you 2, like if x and y were the exact same element, it has to map to the same one. But it has to be most certainly that if they're not equal, that they don't map to the same element in B. And hopefully that's clear, everybody. So in plain language, it's simply saying, every time I put a cat in a box, it has to be that every one of them goes into its own box. That's what it says. If we want to talk about this in terms of cats and boxes. It doesn't have to be like that, just remember. It's just that that's a specific way that we assign the cats to the boxes. Just like we talk about the objects in bins. So another type is called a surjective or onto function. So surjective or onto, I'll refer to as surjective. It means that for all elements in B, so for all of the ones in the second set, B, it has to be that there exists. That means that there's at least one. It doesn't mean that there's a unique one. It just means that there's at least one. So that means there exists an X in the set A so that f of X is equal to Y. So I have a question for you. if these arrows represent my function, how I assign the objects to the bins, is this function surjective? Is this a surjective function? So it's saying for all the elements in B, there has to exist an X so that when you map X to Y, it has to be that this is the case for all of the ones in here. Now, this one is not a surjective function. Notice that this element right here, there is no X to associate it with. Do you see that? There's not at least one X to associate it with. So this is not a surjective function. So this is injective. So this, Miss Kitty, are you having a blast over there? So it's injective but not surjective. Let me give you an example of a surjective function. So now, suppose that we have a different sets A and B. I'm just not going to label them, just to keep this simple. I'll just get rid of the labels on these, just to, not so we don't confuse each other with this. Suppose I have 5 objects and 4 bins. Now, to be surjective means that for every one of the elements in this second set, it has to be that there exists an element in this one so that it maps to that element. So here's a very simple example of how I can get a surjective function. So I take each one of these, associate one with each like this, and maybe I could throw this one over here. So you can think of this, just remember, keep this simple. You can imagine these like your cats. You have 5 cats, you got 4 boxes. You can imagine that these arrows that tell me where the cats go into the boxes is a function, okay? So notice that for every one of the elements here, there is at least one X so that it maps to that element. So this is an example of a surjective function. So this is surjective. However, is it injective now? Is this an injective function? Is this arrow diagram? Is this an injective function? Well, let's think about it. Let's apply the property here. So injective means that for every pair of elements, if they are not the same element, it has to be that they're not equal to each other. So that has to be true for all pairings of X and Y that are in A. So to refute this claim, that means that there exists an X and Y such that they actually map to the same element in B. So if you take a look at this, notice that this element and that element map to this one right here. So it is not injective. It's not injective. It's not injective. Miss Kitty, are you trying to be helpful? So it's not an injective function. Miss Kitty, you're making my writing look like it's melting. I know you're trying to be helpful. But now that I've described these 2 types for you, so I'll refer to these as 1 and 2. If F is both 1 and 2, meaning it's injective and surjective, then F is bijective. Bijective. So we would describe this function as a bijection or a one-to-one correspondence, or just simply a correspondence. So let me give you an example of what one of these would look like. So suppose that I have 4 cats, 4 boxes. Here's an example of how you can assign the cats to the boxes such that it's bijective. So notice that each cat goes in its own box. So this is injective because you can't find me a pair such that they map to the exact same element in B, correct? Likewise, for all elements in the B set here, the second one here, there always exists an X in this first one. so that it get mapped to. So all of these are covered by some element in A, and there's none that are mapping to the same element twice or more in B. So this is a bijection, or the function is bijective. So I must, as I stated previously, not every function is one of these three. Not all functions need to be injective, surjective, or bijective. Here's an example of one that, so this is bijective, just to be clear. It means it's both surjective and injective. However, let me show you that this doesn't have to be the case. So consider this example of where I have 4 cats, 4 boxes, 4 cats, 4 boxes, and suppose that the function looks like, assigns the cats to the boxes as follows. So the first cat gets assigned to the second box, the second cat gets assigned to the second box, the third cat gets assigned to the third box, the fourth cat gets assigned to the third box. Now, let's take a look at our definitions here. Is the function described by this diagram, is it injective? No, because notice that there are 2 elements here that are different. They map to the exact same object. Or, sorry, not object, bin, right? So 2 objects map to the same bin. Likewise, it's not injective. Is it surjective? No, notice that this one right here isn't covered, nor is this one. So this is neither injective nor surjective. So it's not injective and it's not surjective. So I just thought I would give you an example just to illustrate that there do exist ways to cook up functions that are none of these 3 types of functions, using 2 finite sets, A and B. So one thing I really want to emphasize for you is that this isn't terribly strange, right? To imagine a function that isn't either of these 2 categories up at the top, or even the third one, right? So you can imagine I have 4 cats, 4 boxes. It could be that, for example, Miss Kitty and Mochi go in one box, and Pusheen and the other fluffy cat go into another box together, leaving these 2 with nothing, right? That's a possibility that can happen. So the function describes how I assign the cats to the boxes or the objects to the bins. So hopefully this gives you some appreciation for how we can formalize this idea as a function. So let me show you where we can go with this and how you can describe the pigeonhole principle in terms of functions now. So just to get a little bit more formal, let's head over there. So let's talk about this. So just to clarify what we're talking about here, just so you can see what we're talking about, suppose that I have 5 cats. I have 5 cats. I have 5 cats. I have 5 cats. Look at each of these kitties. They're so cute. They don't have whiskers, though. We don't have time for whiskers, nor places for their ears to go in. Okay? So we got 5 cats. And suppose that I have 4 boxes. So I have cats. I've got boxes. Now you can imagine that these cats are my objects. I'm going to call this capital O. It's not a 0. And I'm going to call my boxes capital B. So these are the set of boxes, this is a set of cats. So when I, for example, assign these cats, my lovely, lovely friends, meow, to a box. So when they all get together and they're like, hey guys, let's party, let's get into boxes. So they get in the boxes. How they decide to do this is some function, right? That's what I'm getting at. So let's suppose that, get this one here, that one there, and suppose that these two cats went into the same box. The function f, like I have defined over there, I could imagine this as f, or take some object over here, one of the cats. It tells me the box that cat OI gets into. And all the cats get into some box. So notice that I've just carefully characterized now our scenario that we had, but now as a function. So let's just kind of drop all the fluff, all the fun of this. The fun. So imagine I have now, like we had in our pictures before, I have 5 objects and I have 4 bins. And suppose, I think the third cat goes to the third box, 4th cat goes to the 4th box, then the 5th cat goes to the 3rd box. So I have my objects, I got my bins. These are 2 finite sets. 2 finite sets. And the function I just described here is how the objects get assigned to the bins. So now do you see that actually our scenario is in fact described by a function. So now let's put this all together into the pigeonhole principle in terms of functions. So here's an alternative way to describe the pigeonhole principle now. So just to clarify, what I'm saying is that this is the same concept. There's an equivalency here. Sorry, I got a little excited there. So this is an alternative way of me saying the pigeonhole principle to you. So this is the alternative way of me describing it to you. So remember, in the pigeonhole principle, as I showed it to you, if there are more objects than there are bins, then there has to be at least some bin. There has to be at least one bin such that at least 2 objects appear in that bin. So what does that mean in terms of functions? Well, let's look at this picture, for example. This is just an example, right? So if I had 5 cats and 4 bins, you would tell me, yeah, there's some bin that has 2 cats in it, or more, right? It has 2 or more cats in it. So what would that mean over here then? Let's use our terminology from talking about functions. So remember, the number of objects is more than the number of bins. So let's think about this. And I must stress that if you characterize the pigeonhole principle like this, the proof is very similar. It's just in terms of functions instead. So now I'm going to say for every function f, from a finite set O. Maybe I'll put a fancy little squiggle on that to make it a little easier to tell it's not a 0. A finite set O with n elements to a finite set B with m elements if n is strictly bigger than m, then f is not bijective. It's not bijective. In fact, you can say something a little bit more precise on top of this. So you know for sure there isn't a bijection. Why? Because there's more objects than bins, so you can't match up each one with a bin, right? That would be a nice thing to have. There is no bijection possible here. But there's something specifically that you could say. So if you look at this picture, it's actually not that much different than the example I gave over, let's see. Not that one. There was one actually over here that should kind of harken back to you. So let me just point it out to you. So do you remember that an injective function is one for which if I pick off any two in the first set, they can't map to the same element, right? That's what injective means, right? But notice in my second example here, where I have this description of a function by a diagram, we said it's a surjective function. So notice that every one of these guys here, in this example, keep in mind, as I'm going to explain in a moment, it's not going to be that the function is always going to be surjective either. But notice that we can have it where two elements in the first set map to the same element. And this is a characterization of the pigeonhole principle. So when I say it's not bijective, what I'm actually saying is it's not injective. Meaning that it can be. So this just simply, what I'm saying is that there aren't enough elements in B to be surjective. Most certainly to be injective, correct? Because there's just simply not enough elements. So it's not injective. So it's not injective. However, you cannot guarantee the function is surjective. Let me give you an example of what I'm talking about. So let's head over here. I want to show you just a quick example of what I'm talking about. So what the pigeonhole principle, as I've characterized it here, it says that it's not a bijection. So the function is not bijective because there's simply not enough elements in the B set. The M is too small. You can't form a correspondence. So now that brings us to a fun thing. Can it be that the function is surjective though? Well, some versions of this may be, but you can't guarantee that. Let me give you an example. So notice here that I have 4 objects, 4 bins. Let's throw another object in here. Is the function surjective yet? No, right? It's not surjective still, but it has the characterization of the pigeonhole principle, right? That I have over there. So all you can say is that it's not bijective, and in particular, it's not injective. That you can say for certain, but it may or may not be surjective. So hopefully that is clear. So the whole idea is just when we talk about our objects and bins or cats and boxes, it can be characterized in terms of asking if there is a bijection from one finite set to another. Pretty fascinating stuff, right? So if you're wondering how you prove this, as I mentioned just a moment ago, the proof is very similar to the one I gave you with our objects and bins, except it gets clarified or stated in terms of the definitions of these things more formally. Namely, what a bijection is, and then you lay out the formal notation for that in terms of functions. Otherwise, the argument is essentially the same. So if you're curious about that, feel free to bug me, but you'll find that the argument that I gave you with objects and bins, it's the same idea. It's the same idea. It just has less of the function formalisms, okay? So that's the pigeonhole principle, everybody. Are there any questions? Any questions at all? So that's what the pigeonhole principle is about. Are there any questions before we start talking about things we could do with the pigeonhole principle? Hopefully you enjoyed the kitties running around. They're having a blast down here. Maybe I'm going to take the big box down. But I'll keep, see, I'm tempted to keep it here, but I think it might loosen up some environment that we have here, because we have quite a few things going on over here. If you've seen what it looks like over here, it's like a whole, I'm surrounded by everything, okay? I'll keep the box here just as a reminder, okay, everybody? That way, I think that's helpful for us. So I'll keep the box here just in case. So, but I'll keep the kitty here. So we're going to keep a kitty over here. But I'm going to erase the boards. But are there any questions about the formalization of the pigeonhole principle? Or just when we think about it as objects or bins? So I thought I would show you just kind of two different ways of talking about the pigeonhole principle. So you might say, Dan, why did you show us this thing about functions if we could just talk about objects and bins? Well, think about it. When we talk about the objects and bins, we're putting the objects into the bins, right? We're forcing each object into some bin. But this is characterized by a function. So this gives you an exact way of talking about what exactly we mean by putting an object into a bin. That's why I showed it to you. Otherwise, somebody could fudge around with the pigeonhole principle with you, saying, oh, well, I'm putting an object into a bin. See, the reason why, that's why I'm bringing up functions for you. That way you have an idea of what exactly we mean by putting an object into a bin. We're assigning it by using a function. And you might say, Dan, why do we need a function to do this? Well, it's just an exact way to talk about the same thing. That's really it. So just in the same breath, if, for example, and I'll talk about an example that involves scheduling a little later. But what we could talk about even, for example, is if I assigned jobs or tasks to be assigned to machines or agents to be completed for our schedule. Like say if you're working at a place and you're assigning tasks for workers and you want your workers to finish all their tasks in the shortest amount of time possible among all your workers. We're actually going to see an application of some of these ideas in such a setting. But I wanted to mention that is because you could describe the assignment of the task to the workers or the workers to the task, depending on how you want to formalize this issue. Say we think about it as jobs and machines, for example. That's how a scheduling theorist might think about this. If you have a function, you can describe the function describes how you take each job and you assign it to a machine. So you map a job to a machine, just like we talk about our objects and bins. So you could describe this more formally using a function. So hopefully that is clear this is why I wanted to show you this. So somebody can't fudge with you what they mean by this whole, oh, we're assigning some object to a bin. Okay. So now we're going to get into some fun, okay, everybody? So now that we've talked about what the pigeonhole principle is, we could use the pigeonhole principle in all sorts of different settings. So let me figure out where we're at. Okay. So anyways, so let me just write down the pigeonhole principle for us again. That way we have it in front of us. The pigeonhole principle. So we're going to let n be a positive integer. Suppose there are, sorry, just Give me one moment. I'm just checking one quick detail here. Just don't want to... I have something rattling over here I just want to take care of. Okay, I think that helps. Yeah, there we go. That's much better. My apologies, everybody. So I'm just going to write down the pigeonhole principle here. So suppose there are at least my rattling thing. Man, this is funny. I have something rattling over here. I got my little bird friend rattling over here. And for some reason what I have there to obscure the rattling keeps falling down. So let's try this again. Suppose there are at least n objects. Suppose there are at least n objects and m bins where n is strictly bigger than m. I'm not going to worry about it. I think we're okay. Then there is a bin with at least 2 objects. Just give me one moment. I just want to just stare at this and like, gonna see if I can get this to work. My apologies, everybody. Just dislike when our lesson gets disrupted by little bits of things. I'm just gonna take my little birdie friend. See, my little birdie friend's rattling over here. I'm gonna put my little friend over here just for now. Bye-bye, my little penguin friend. Just for now. So that way it's not rattling. Okay. So, let's get back to where we were. Okay. So previously we had seen the pigeonhole principle. We proved it. We've seen 2 different ways of formalizing the pigeonhole principle, namely in terms of objects and bins. And we also talked about, with some discussion about functions, how we could describe the pigeonhole principle in terms of functions. Namely that the pigeonhole principle, instead of talking about there being a bin with at least 2 objects, in that case it's that there is no bijection, meaning it's not bijective. So, I want to show you a couple of basic examples first, just so we can see what we can do with this pigeonhole principle. So I thought we would start off with some examples. And one classic way of playing around with the pigeonhole principle is by taking large number statistics. Suppose that I give you a group of people. I would like to be able to say something about that group of people with respect to some category that all of these people have. So let's start with a basic example. I'm going to refer to this fun bit of discussion we're going to have as meeting of birthdays. So as per usual, if you want more discussion about some of these things, they're in the notes, okay? So I'm sure if I gave you a group of people, we can agree that everybody has a birthday. So everybody has a birthday. I mean, even including you guys, those ones on the leap year. I understand. Everybody has a birthday. The day of the year that person is born. So days in a year are organized by month, right? In the Gregorian calendar, there are 12 months. We're going to refer to the birth month as the month for which a person is, the person is born within, okay? the birth month, sorry, I'm getting really excited here. The birth month of a person is one of the 12 months I'll say they were born in. I'll say a person. We'll say a person was born during. For example, if you're born in the month of March, your birth month is March. Hopefully that's clear, everybody. So if I give you a group of people, suppose I bring together a group of 13 people. So suppose that we're given, sorry, I'm getting really excited. My given is sort of melting over here. So suppose that we're given a group of 13 people. I have a question for you. If I give you 13 people, any 13 people, I have a question. Question. Do at least 2 people share the same birth month? So if I give you 13 people, do there exist at least 2 people that share the same birth month? Well, let's see. Let's try to kind of visualize this a little easier using some of the things we've talked about previously. So I have 13 people. We have 12 months. So I'm going to have some people. So I have these are going to be my objects. So I'm going to have 13 of them. I have person 1, person 2. I'm just going to assign them names just to make this easier to play around with. Person 12, person 13. So I have 13 people. This is my group of people. And also I have birth months, right? And these are my bins. So let's see. So we got January, you got February, you got March. I'll keep it. I have to pick either abbreviations or full, so I'll go abbreviations here. March all the way up to December. We got the 12 months. Those are our bins. And we agreed that everybody has a birthday, and it's going to fall, like whether you want to round it or not, regardless. Somebody's got some birth month they can associate themselves with. So let's describe how that might play out. So I can have each person is going to be associated with a birth month. More formally, I could describe this actually as a function if I wanted to. So I'm going to call the function capital P. It's going to take in a person as input. No, don't think about like the machine picture. It gets a little graphic. Let's try to just imagine it more that we just know that each person has a birth month. Okay. So this is the birth month. So it just tells you the birth month of person PI. So it tells you the birth month of person PI. So you could imagine it's just like a table with all the people in this group. Each one, it tells you each person with their birth month right beside it. So you can just imagine it's like a lookup table. So we've identified objects and we've identified bins. We've identified how we're going to put the objects into the bins. But what can you say about our objects in bins now? Well, normally a good strategy for applying the pigeonhole principle is to identify the objects, identify the bins, and identify the relationship between the objects and the bins. If it characterizes the pigeonhole principle, then you're all hunky-dory to play around with the pigeonhole. But you have to be very careful when you use the pigeonhole, because remember, these are objects, those are the bins. I need to be able to put the objects into the bins. It isn't that I get an option to not put them in the bin, right? They all have to go into some bin. Like, everybody here has a birth month. Nobody's just gonna be like sitting off to the side saying, I don't have a birth month. And remember, the beauty of the pigeonhole principles, I don't know how these exactly are assigned. I could, for example, hypothetically speaking, I can have a group of 13 people where everybody is born in January. That is a possibility. Likewise, there could be somebody that like half of them are born in September, half are born in, I don't know, in April. That's a possibility too. These are all different possibilities. The pigeonhole principle, however, tells you that there's going to be at least one birth month that has at least 2 people that share that birth month. It's because they're birthdays during that month. So yes, by the pigeonhole principle, at least 2 people in the group, just to be clear. Not just any 2 people, it's just in this group of 13 people shared the same birth month. Pretty neat, right? That's a pretty good place for us to start, right? Like the whole idea is that there are not enough birth months for my people to all be able to be distributed such that they're all in their own birth month. Does everybody see that? So notice that you can also extend this. So if you wanted to have 15 people, the fact is still true, right? As long as there's at least 13 people, you can get away with this. Now what if you had it, let's ask a similar question. They share the same birth month, but how about the same birthday? How about the same birthday? Can we say that? Using the pigeonhole principle? Any suggestions? Can we use the pigeonhole principle here? It's instead of asking the question, if I give you 13 people, any 13 people, and I ask the question, are there at least going to be 2 people that share the same birthday? Can you guarantee that under the pigeonhole principle? Well, let's think about it. Let's look back at how we characterize the objects and bins. Because remember, the objects are the people. The birth months were the bins. Now, for this question, we'll need to swap out the birth month with the birthday. So, can we use the pigeonhole principle to justify that there's at least 2 people in any group of 13 people that they share the same birthday? No, right? That we don't have enough people to guarantee such a thing. Because when we swap this over to birthdays, so when we have birthdays, now I'm talking about a day during the year. So we're talking like January 1st all the way to the last day of the year. Now, how many days are there in a year? At least in the Gregorian calendar. Now, I'll warn you that this is a little bit of a trick question. I'll give you a moment to think about it. So, while you're thinking about that, I can answer this question. You can say no, because we just don't have enough people. But I want you to think about that. Not enough people. Now, how about if I generalize this question a little bit further for you? Just to make it a little easier to answer the question. Okay, what about if it's an arbitrary year? Not just, say, a year where a leap year isn't. What if it is the case that we land on a leap year? That means that, suppose that there is a day for which we have an extra day in February. So, how many people then do we need to get together? At least for any arbitrary year. So, how many do we need? So, that's the question. Because we lack a number of people. So, the days in the year. So, how many days in a year? Well, on a typical year, if we're talking like physics, it's approximately 365. It's an approximation of this. But what happens as a result is that in the calendar, what happens is every so many years, we have to make up for that little bit that's on the end of 365. And that's why we have leap years. So, but because of that, this is at most 366 days in a year. So how many people should I get together then to guarantee we can use the pigeonhole principle? So think back to my picture up there. My bins are the birthdays. So the days of the year. Well, now you could see that the number of bins is going to be at most 366. So if I give you 367 people, that will be enough, regardless if it's a leap year or not. So if you get me at least 367 people, that's enough to think about. So I'll let you think about that. In fact, I encourage you, if you could somehow get 367 people together, I can't today. I can't fit that many people in this room, okay? It's not that big. If I could, we could take 367 people. We can ask them what day of the year they were born. And the pigeonhole principle guarantees at least 2 of them are going to share the same birthday. Pretty nifty, right? So do you notice the exercise is quite simple? But you have to be very careful, right? Because remember, it's the kind of relationship that exists here. Is that every person has a birthday. Every person has a birth month. Every kitty has a box. That's what we're talking about here. So the point is that we have to identify the objects, the bins, and then there's going to be some function that's underlying this that is going to describe how we assign the objects to the bins. Or equivalently, one finite set to another finite set. And then we check the conditions of the pigeonhole principle. And I must stress that this is just some basic application of the pigeonhole principle. You can use it in much more sophisticated ways, as we're going to see in some of our examples. I'm not going to go crazy advanced today, but most certainly we can do some nifty stuff with it. So that's one neat example, but let's go even further than this. So let's go further than this than just thinking about birthdays and birth months, okay? So let me take this one step further. You thought me bringing a group of like 300-something people together might be a pretty interesting task? What if we do hundreds of thousands of people? So let's have some fun with that. So just remember, the pigeonhole principle says that if there's at least n objects and m bins where n is strictly bigger than m, then there's going to be a bin with at least 2 objects. So just remember that. So that's what the pigeonhole principle tells us. So let's apply it to on a larger scale. So I'm going to take and address this question to Winnipeg. Got some lovely Winnipeggers. For those that aren't aware, a Winnipegger is someone that lives in Winnipeg. So let me let's talk a little bit about this. Let's do this. So at the time of making this video, and I must stress that technically it might be more depending on how generous you want to be about the boundaries of Winnipeg. You can always use some more up-to-date statistics from Statistics Canada, for example, if that is something that you need. But the population of Winnipeg is at least 713,000 these days. Now, here's another thing. So this is just a fact. You're more welcome to check it. So it's at least that many. How about this? Now, let me throw another interesting factoid to you. Now, you'd agree with me that humans have hair on the top of their heads. They may have no hair. They may have at least one hair follicle on their head. They may have more, right? The point is every person, including every Winnipegger, has some number of hairs on the top of their head, right? So this is just fact 1. Fact 2 is that humans on average have 100,000 hairs on the top of their head. This varies depending on your hair color, for example. From at least what I've read, and I had to do a little bit of digging for this. From my understanding, depending on the color of your hair, at least on large population averages, the amount of hair follicles you have can differ. For example, a blonde-haired person may have more hair than somebody that has brown hair. At least on the top of their head. That's at least what we're talking about here. But, so it may be up to, for this average, for 150,000. That's namely for the blondes. So regardless, I'm just going to be overly generous, and I must stress that if, say, for some reason there's somebody with even more hair follicles than this, the argument will still hold. It doesn't matter that I just picked this number. It could be even higher. It doesn't have to be that much higher than this. You can go up to 300,000 if you wanted to. I'll just make it this is at most 200,000 hairs. It's definitely a bound that's going to be okay enough for us, at least here. But if you want to make this 300,000, you want to make it 400,000, if you want to make it 500,000, that's okay too. Like I said, it's usually if you look at the surface area of somebody's scalp, you could do some basic calculations from physics and you'd find that, yeah, it's roughly something like this. So to expect it to be somewhere way out here is going to be quite the anomaly. But the point is that that number over there doesn't matter a whole lot. I could easily made it 300,000. The argument doesn't change for what we're going to talk about here. So, anyways, is that every Winnipegger has 0 or more hairs on the top of their head. So you have an idea where we're going with this. So, you could imagine I gave you the people of Winnipeg. So remember, we identify the object, identify the bins, and the fact that every Winnipegger has to go into one of these bins, because it's quite natural we're going to talk about Winnipeggers. So we got our people. So these are my objects in the example. Objects. And we're going to have hairs on the top of your head. These are going to be the bins. Now remember, there could be somebody that has no hair on their head. They're bald. Or they have some small number like me. Some smaller number. But the point is, we're just going to be generous. We'll throw some more categories of numbers of hairs in there as well, just to play it safe. But keep in mind that number could always be higher if we wanted it to be. But not too much higher. But if you understand how we're going to use the pigeonhole principle here, if we can, you'll see that it really doesn't make much of a difference. So I'm going to label out the people. Okay. So I've got my people. I got hairs on the top of your head. So how am I going to describe this? Well, we said that every Winnipegger has 0 or more hairs on the top of their head, right? So let's describe this now. So T of PI is the number. So for a given person, it's the number of hairs on top of PI's head. Which makes sense, because every one of the Winnipeggers has some number of hairs, whether it be none. And I must stress that the argument I'm going to present to you doesn't matter if we even just ignored all the bald Winnipeggers. But the point I'm getting at is that if the population of Winnipeg is at least 713,000, it could dip down a little bit if you wanted to. It may or may not. Not sure. I can't tell you the future of populations, okay? But the population of Winnipeg is at least 17,000. Sorry, not 17,000. Holy jeez, that would be horrible. Imagine doing snow plowing that. But there won't be enough people to do snow plowing, okay? There's a lot of snow that comes in Winnipeg during the winter, unless everybody's snow plowing. I'm just kidding. I'm just kidding around. We're having some fun here. So I'm going to throw some fun facts at you. The population of Winnipeg is at least 17. Sorry, not 17. The population of Winnipeg is at least 713,000. Humans on average have about 100,000 hairs on the top of their head, but it may be up to 150,000 on average. But for generous, we're going to keep it at most 200,000. Well, the people are objects in my application of the pigeonhole principle. The number of hairs on the top of your head are bins, and the number of hairs is simply characterized by this function. Because every Winnipegger has 0 or more hairs on the top of their head. Like me. I don't have as many. But the point is that you get a very, very interesting revelation that comes out of this. Is that, so by the pigeonhole principle, at least 2 Winnipeggers have the same number of hairs on the top of their head. Have the same number of hairs on the top of their heads. We'll say head. pretty wild stuff if you haven't thought about that. The whole point is that we have enough people to allow us to say things like this. In fact, if, say, for some reason, I don't know, somebody genetically was mutating people to have more hair, like more hair follicles on their head, or physically increase the amount of, well, the density of your hair follicle, like the amount of hair follicles you could fit in a given space, say they're like extremely fine, for example, somehow, I don't know, and you increase this number, you can increase this number quite a bit, right? Because that number is quite a bit bigger than that, right? So just to summarize, if the population of Winnipeg is at least 713,000, and the number of hairs on the top of your head is definitely at most 200,000 hairs, in fact it could be more if you want, the pigeonhole principle tells you at least 2 Winnipeggers have the same number of hairs on the top of their head. And this is true even if you discard the people that are bald. So people almost approaching me, okay? We're cool like that. Pretty fascinating stuff about the pigeonhole principle, right? So those are some interesting examples of how we can apply the pigeonhole principle for large groups. This is one way you can use the pigeonhole principle. So, for example, if you're working with ingredients and you're asking how many ingredients you have to fit a certain number of pizzas, or something along those lines as well. Like, there's a lot of ways you can pack things from items into bins or objects into bins. This sort of packing stuff I think about all the time. But the point is that you can apply the pigeonhole principle when you have sufficiently many objects to characterize the pigeonhole principle in a rather natural way like this. And you get really mind-blowing conclusions kind of like this, that you never really think about in your daily life. So are there any questions? Any questions at all? So isn't that neat? So you could, and keep in mind, this is just one intellectual exercise. I could have easily swapped the cities. I could have easily have, instead of talking about, well, hair follicles are interesting because they could vary between people. But you could say all sorts of interesting things. You could talk about the number of dolls each house that somebody lives at has, for example. You can talk about all sorts of different categories. You can talk about the number of cats they have. And like ask how many people do you need to make that work. So this is one way you can apply the pigeonhole principle. So what you're going to see actually in the next coming example is that and tradition with Dirichlet, is that we can actually apply this to number theoretic properties as well. So I'm going to give you, our next example is going to be involving number theory, and I'm going to show you some interesting facts about number theory. And we're going to use that to prove an interesting claim about the divisibility of numbers. So I could give you an arbitrary set of numbers, and I could tell you something about their divisibility, even though they could be an arbitrary set of integers. It's just kind of wild if you think about it, but at first it's like, okay, well, I'm gonna show you that this example, sure, you'll be able to identify the underlying structure of the pigeonhole principle once you see where we're going with it, once I lay out the game plan. But the point I'm getting at is that once you really work yourself up to this level, there's gonna be some examples where the pigeonhole principle is not nearly as obvious to apply. So I'll give you an example of one of those. It's not terribly difficult. It's arguably one of these cute examples that somebody would give you if you were talking about graph theory. So I'll give you one application for graph theory later. But namely, I'm going to give you an example before that how you can apply it for other number theoretic claims too. Like if I give you pairs of numbers, how can I know that there's at least two pairings or a pair that could go together that sum to a number? How can I guarantee that some set of numbers has this property? So we'll see an example of such a thing. So let me just erase the board here. Let's think about this. I don't know if Miss Kitty is deciding she wants to come back or not. Miss Kitty's up to something. I don't know what. So just erasing the board, that way we can get to our next example. So our next example is going to be far more involved, where we're going to actually prove a claim, not just simply apply the theorem. We're going to have a step in our proof that's going to use the pigeonhole principle. So as I mentioned just briefly, maybe a little while ago, I mentioned that the pigeonhole principle can be used in different kinds of arguments. I'm going to eventually give you an example where you can see how we can apply in a couple different ways. Prove the exact same claim. Hello, Miss Kitty. Miss Kitty, you going to say hi to everybody? You going to say hi to everybody? Miss Kitty, what are you doing? What are you doing, Miss Kitty? I don't know what's going on. Meow. Miss Kitty, are you watching? Are you trying to watch these people? These lovely, lovely people? Okay, I'll pet you. But you got to behave yourself. What, Miss Kitty? Why are you knocking the box over? What did the box do to you?
0 bits.
What did the box do to you, Miss Kitty? Pet the kitty, okay. Ah! She's biting me! Ah! She's biting me! She's really hugging into me right now. Here, I'll bring the Miss Kitty closer. Come here, Miss Kitty. Come here. Ah! Got her. I'm gonna break the fourth wall, everybody. Prepare yourself. Which way are we going?
Chaos that is Miss Kitty.
Go, Miss Kitty. Miss Kitty, kitty. There we go, Miss Kitty. See, you got your attention? Is that your mission in the world, is get everybody's attention? But are there any questions? Did you find the hair follicle thing rather interesting? That we've seen how we can get an interesting conclusion like that just by applying the pigeonhole principle. And like I said, you can use this in all sorts of different settings. Just the whole idea is that there's more things than there are things you can put them in, okay? That's the whole trick. And remember, it doesn't tell you which bin it goes in, right? For example, just like we're talking about hair, numbers of hairs on the top of your head, the pigeonhole principle doesn't tell you which category, the number of hairs, that at least two people fall within. You would have to examine this. So you would have to check. Unless you're using some stronger conditions for which you can guarantee such a thing. Miss Kitty, can I have my notes back? Am I allowed to have my notes? Mer? Yeah, she's going bonkers. Does anybody have any fun questions while Miss Kitty is distracting everybody? Miss Kitty, what did I do? She's just going bonkers. Hey! Ah! What are you doing? What are you doing, Miss Kitty? What did we do, everybody? Ah! She's really hugging me. Ah! Ah! She's going bonkers. Miss Kitty, what are we doing? Now, can we get to our next example, Miss Kitty? She's really aggressive here at the moment. I'm sorry, Miss Kitty. I'm sorry you're so excited. Are you excited about the pigeonhole principle? Hey, those are my notes, Miss Kitty. Give me those notes back. These are the notes for our next... Miss Kitty, are you going to show everybody the notes? Are you going to show the next example, Miss Kitty? I think she's very enthusiastic about it, okay? She's just going wild here at the moment. Okay, so if there aren't any questions, let's get to our next example, everybody. So let me just
Miss Kitty loves the mathematics cause she knows it unlocks the universe.
She does. Yeah, no, that's exactly it. That's exactly it. Miss Kitty, we're going to get to our next example. Are you going to behave yourself? What if I give you a box? Let's try giving her a box. Maybe that'll be a good peace offering for her. Here's a box. There's a box. She's huffing the box at the moment. Here, you want to go?
Understand cats understand physics on a level humans just can't process.
Now get in the box, Miss Kitty. Get in the box. You want to get in the box?
Heck, even
No.
ninjas understand quantum mechanics much better than we do.
Okay, how about let's get the bigger box? Because this little box ain't gonna cut it. Let's get the bigger box back. Maybe that'll distract her enough. She's really in a mood at the moment. Okay, here we got our bigger box. Let's get some kitties out here. Miss Kitty, you want to get in the box? The answer's yes. The answer's yes. Okay. So I'm just going to move this a little bit forward. That way we aren't blocking the board at all. So let's get to our next example. So if Miss Kitty decides to disrupt everything, that's okay. It's part of the fun, everybody. I know you guys love Miss Kitty. So let's get into this. So the pigeonhole principle can be used for all sorts of different things, particular discrete objects like we've talked about previously. We've seen examples that use large populations or large groups, and just applying the pigeonhole principle is sufficient. I want to show you an example that's a little bit more classical, as in the sense that a lot of the earlier examples of using the pigeonhole principle were associated with number theory. So I'm going to give you an example that's a number theoretic example. Now, to do this, I'm going to give you a little bit of number theory that we are going to use to prove a claim for which the pigeonhole principle is going to be very helpful for us. So, just the first thing I want to talk about is if I give you an integer. So, if I give you an integer n, we say that it's divisible, just to give you some fun here, we say that n is divisible by n, which is going to be a positive integer, right? So either way, it's not 0, right? It's divisible by n, which is a positive integer. There is some integer k. There is some integer k such that n is equal to k times d. So it's got the kd like the K at Kraft Dinner. Miss Kitty took a ride, everybody. She's okay. She took a ride, everybody. She's okay, everybody. Miss Kitty, you doing okay there? Yeah, she's okay. She's okay, everybody. She'll be back. So, anyways, we see that an integer n is divisible by, d. We want d. By d. See, this is what Miss Kitty does sometimes. So, an integer n is divisible by d if there exists, if there exists some integer k such that n is equal to k times d. So you could think of k as that multiple such that you multiply it by d to get n. So this is some pretty basic stuff. At least I think it should be. Now, I'm going to present you a theorem that's going to take advantage of what we know about divisibility. So I'm not going to prove this theorem for you, but it's a very helpful number theoretic theorem. So it's very often called the quotient remainder theorem. I'll abbreviate the QR part. Quotient remainder is QR. And it's stated as follows. So given any integer n, and positive integer d, there exists unique Q and R. So these are unique. So these are determined by N and D. These are unique Q and R that are going to be integers. So that N is equal to D times Q plus R. And it has to be that the R value, so what R is between 0 and D minus 1. So it has to be less than D. So keep in mind that we're putting this in the context of us talking about divisibility. So we're talking about if I give you N and I give you a number I want to, like, say, for example, to divide by D, for example. So the idea is that I have two unique, so determined from N and D, two unique Q and R, so that you could rewrite N like this. So N is going to be some multiple of D plus something called R. Now R, I gave it that name explicitly for us here because this is the remainder. So that's the part that's going to be important for us for today. So we call that the remainder. So you might know that phrase from somewhere when we talk about division. Now, if you, for example, say, for example, you learned long division, you may have learned something called the remainder. So when you carry out long division, you end up with something at the end called its remainder. It ends up being an integer. So that's what R is. So just as an example, just to illustrate what I'm talking about here, I'm not going to do long division here, but this should illustrate the idea. If I give you a number like 5, and say, for example, I want to consider, if I wanted to rewrite this, I could rewrite it like this. Say if I wanted to see if I took 5 divided by 2, how many times can 5 go into 2? Twice, right? Because 2 times 2 is 4, but you can't go up to 6, right? So it's 2 times, so I could rewrite this as 2 times 2 plus 1, right? 1 would be the remainder. So if you divided 5 divided by 2, you could put 2 in twice into 5, and then you end up with 1, which ends up being, when you take 5 divided by 2, what do you end up with? You end up with some fractional part. That ends up being that corresponds to this remainder here. So you can see, okay, well, it's 2.5, right? Half of 5 is 2.5. So notice that when you take and you rewrite, so you keep in mind that when we talk about this, if you were to say, hey, okay, I want to take whatever 5 divided by 2 is, if I round that down, notice that the closest multiple is sitting right there, right? So that's what Q is. So that's what the quotient remainder theorem tells you, is that if I give you N and D, or you imagine that we're talking about divisibility or so, I'm saying that N is divisible by D in the sense that I'm talking about here. Now, I'm not saying that it is divisible. I'm saying that N is assumed to be at least D, just to be clear. So that means that we can have these unique 2 values, and I can rewrite it like this. So is that clear, everybody? That I can, and we've seen this example with 5. Let's do another example. I could take an integer 6. Let's do -6. because it's for any integer. That includes negative ones too. So that means that I could take, and suppose I want to do 6 divided by, so think about this in terms of how I could write this. So if I give you, say, negative 6, and let's go 5. Let's go 5. So it says d times q plus r. So I have 5. Now how many times can negative 6 go into 5? Well, 1 less, right? So remember, because q and r are integers. Specifically, q could be any integer. So that makes it negative 5. And then, actually, no. Do we want it to be negative 5? Let's think about it. Because we know the remainder, we're not going to be able to put it all the way through, right? So we might need to bump it up a little bit. Let's think about this. I'm having a bit of a brain fart at the moment. Let's see. We have... Are there any ideas, anybody? Well, let's think about it. We could find a different... Negative 1 might not be... It might be not small enough. Let's go negative 2. Then we get negative 10. Then we add... Now we have some number between 0 and d. D is 5, right? So we can bring this down by... so I have negative 10 plus 4, for example. So notice here that I have negative 10 plus 4, that's negative 6, as desired. So what the theorem is saying is that if you give me an integer and a positive integer like this, there's going to exist these two numbers here, q and r, such that r is between these two values. So it's 0 up to d minus 1, one of those values, and you could write n like this. The point is that this r bit is the remainder, which if you think about it carefully, this isn't very terribly surprising, given that this is a negative number, and if you try dividing this like so, you have to sort of work backwards to make this work. It's a little bit strange. That's just sort of a nature of when you start playing with negative numbers as opposed to positive ones. So, for example... I'm just trying to think about this in my head before I say anything too fun. Like, I'm having a little bit of fun here with everybody, just to be clear. If I have... Because you got to think about this also like a number. Like, if we have numbers like this. So here's 0. Like, suppose that this is 6. Actually, no. Let's make it 5, because d is 5. So this is d, that's 2d. This is minus d, this is minus 2d. And you think about this in terms of increments. What the theorem is saying is that there's going to be some way that you can identify some q. So there's going to be some q that tells you where the closest d will be. And then you could go r away from that. So in our example here, we had 1 minus d away. So I bring this over by r, some value r. In this case, it was 4. So notice that it's because of how close the numbers can be away from the next multiple. R is kind of like that little adjustment that gets you to the number. If it isn't actually divisible by it. Hopefully that's clear, everybody. So let me just... wait, I want to keep that. N is equal to KD. My apologies. So does everybody understand the theorem? I'm just going to erase the board. Just remember that we can write any integer based on what's kind of close to its closest multiple plus a little bit. But that little bit can't be any more than d. It has to be strictly less than d, because otherwise you get to the next multiple. So you can look at the remainder sort of like a way of adjusting a little offset to get to the value if they aren't a multiple of. So it's not it's a multiple of D. So we're going to see how we're going to use this QR theorem to help us, the quotient remainder theorem. So here's the claim. So here's a theorem. We're going to let n be a positive integer. For any set of integers, I'm going to call this set A. It's going to have A0, A1, A2, all the way up to AN. It's going to have n plus 1 integers in it. With n plus 1 integers, my eye's sort of melting there. Not this eye, that eye. There exists two integers, AI, AJ, which are going to be in A with I not equal to J. This is just to guarantee that they're not the same element. Such that AI minus AJ is divisible by n. So when you see this, you're looking at this like, well, I see some things that remind me of the pigeonhole principle. You see something that's slightly, like it looks like n plus 1, which is like one higher than a something, right? So that's like the first thing that might glare at you when you see a statement like this. However, other than that, it doesn't look really clear at all what exactly we would need to do if we wanted to use the pigeonhole principle. And I must stress that this is just one example. The pigeonhole principle may not apply at all to your given problem. This is just an example showing you kind of the mindset, the mentality you might go about when we're thinking about kind of number theoretic claims, asking questions about divisibility, for example. So here's the game plan. And it comes down to how the QR theorem, the quotient remainder theorem, works. So what did the quotient remainder theorems tell you? It told you that if I give you any two numbers, in particular an integer n and a positive integer d, what it did was it told you that there's only certain numbers of remainders possible, right? So what did the QR theorem say? So the game plan I have in mind is that the remainder is going to be something between this, right? It's going to look like this, right? But those are all integers, right? Those are all integers. But what does that actually look like? And remember, D here is, that's the number we're talking about for divisibility, like the closest multiple. And at least that's the intuition that we had. Over there, it's n, right? So, but just to keep it simple, I'll just keep D over here. That means that the remainders can only have these values. How many are here? Well, that's D many. There's D many possible remainders. And that's the other ingredient that we're going to need here. Does that give you any ideas what we might try to do here? So remember, any integer, when I use the QR theorem, it says I could rewrite it by some multiples q of whatever I'm dividing by, plus a remainder. And the theorem says that the remainder is somewhere between these two values. That means that it has this many possible values, because it's an integer. So let's use this now. So let's take these two ideas together. We're going to try proving the claim. Observe observe that any integer divided by n by the QR theorem has remainder R that satisfies 0 is less than or equal to R is strictly less than n, because that's what D is. So we're going to comma, let's put a comma there. We're going to let this be a set. We're going to call it R. So this is just going to be a capital R here. It's going to be the numbers 0 all the way up to n minus 1, akin to what I wrote over here. So that's a finite set, right? So each integer of A, and remember the statement is about any set of n plus 1 integers. These could be negative, they could be anything that is an integer. There's nothing saying that, oh, this number has to be less than that number. No, these are an arbitrary set of integers. That's the wild part about this. So just watch. So each integer of A, when divided by n, has some remainder in R. This should remind you a little bit of what we talked about for tips for applying the pigeonhole principle. So far, we have A, we have R, and we also have this thing saying that every one of the integers, when I divide them by n, has some remainder. So every integer has some remainder. Right? That's because that's from the QR theorem. So, that tells us something. Well, how many integers are there? There's n plus 1 integers. How many integers are in this set over here? There's n of them. There's one more than the number in this set. So we could use the pigeonhole principle. There are n plus 1 integers. There are n plus 1 integers in A, or elements, and n integers in R. So, by the pigeonhole principle, at least two integers, that integer is sort of looking like it kind of stayed outside a little too long out in the cold weather. AI, AJ in A with I not equal to J, because they're two different elements, right? Have the same remainder. So there's going to be two of the elements in A that have the same remainder when divided by n. Now let's bring this all together. So now we know that there's at least two integers in the set A that have the exact same remainder. So now we're going to use this information carefully. Now, the QR theorem was helpful for us for this detail, right? We're going to use it again to now write those two integers. So now we got these two integers here, II and AJ. I would like to know what's going on with those two. So let's take a look at what's going on with those two. So we're going to use the QR theorem again. So applying the QR theorem. Now we're going to just rewrite what those two integers that we derived, or what we obtained. We're going to take those two integers we obtained, we're going to apply the QR theorem to each one. There exists. Why? Because the QR theorem says that there's that integer q, and then there is the integer that's the remainder, right? They're unique. They get determined by in this case, this would be that integer in the set A versus n, which would be the positive integer here. There exists q1 and q2. So I'm going to have two of them because I'm going to use the definition twice technically. So these are my multiplicative numbers, or multiples, and integers. We're going to have R1 and R2. They're going to be the R2 remainders. They're going to be between 0 and n. Well, 0, but it includes 0, just to be clear. So that AI is going to be equal to Q1 n plus R1, right? That's what the theorem says that we could do, right? Is we could write it by some multiplicative closest multiple plus the remaining bit that gets me to AI. And we can do the same thing here. AJ is Q2 times n plus R2. And now I'm just going to take the difference between AI and AJ, right? Because that's really what we're curious about. Because I know they exist. I don't know which one it is in A, those two. I don't know which ones they are. But I know they exist. Like I said, it doesn't have to be constructive. And by taking their difference, I'm going to take AI and subtract AJ. And watch this. You're going to see a definition pop up that'll remind you of something. So let's watch this. So watch this carefully. I'm just going to write what each of these equations tells me AI and AJ are. Q1 times n plus R1 plus Q2 times n plus R2. Well, these both have, like I could just drop these parentheses and notice I have Q1 and Q2 that they're both related by n. So I'm going to factor there. I'm just going to regroup the remainders together. And then you end up with the following. This is equal to Q1 minus Q2 times n plus R1 minus R2. But what did we say about R1 and R2? What did we say about those two? What did we say about those? What did the pigeonhole principle? Why did we use the pigeonhole principle? We showed that these two have the same remainder, right? That's why we picked AY and AJ the way we did. So these two are actually equal to each other. R1 is equal to R2. That's because we used the pigeonhole principle to say that there's at least two integers. It's these two right here, right? That have the same remainder. But that means that this right here, what does this equal? That's 0, right? Because it's the same number. So it means that this is actually equal to just Q1 minus Q2 times n. Are we done yet? There's something that we're not technically done yet, but there's something very important I want you to observe about this. What did we say for an integer? So if I give you an integer, now keep in mind that AI minus AJ is equal to this. So what did it mean for me to say that AI minus AJ is divisible by n? What would that mean? Remember, we said that there exists an integer such that that integer times n would be equal to my number. Is Q1 minus Q2 an integer? Yeah, because it's an integer subtract another integer, so the result of that is an integer. So this is, that's it. This is an integer, right? Therefore, since q1 minus q2 times n is divisible by n, ai minus aj is also divisible by n, and that completes the proof. Piece of cake, right? So notice the strategy. All we did was now you might say, Dan, how did we know to use the pigeonhole principle here? Well, normally when you play with a statement like this, you have to be careful, and it's about identifying key aspects of the statement. Because proving things ain't easy all the time, believe me. You can spend months, even years, focusing on one statement and seeing if it's true or not. But this one is really nice because we identified those key couple observations. Namely, the number of elements that were in the set A, right? The next thing we also observed was about the quotient remainder theorem told us about the number of remainders that were possible. And then we tried to associate each integer in A with one of its remainders. Well, each one has exactly one, right? Because it's unique. So remember, that's a part of the quotient remainder theorem. So that means that when we talk about that, each integer in here has a remainder. And there's one less remainder than possible at most compared to the number of elements, because there's one more. So keep in mind, you could not use the pigeonhole principle if there's one less element in this set. That's really one thing I really want to point out to you, is that because otherwise we couldn't use it because it doesn't meet the conditions of the pigeonhole principle. But once we did that, we were able to identify AI and AJ as per the statement, because it was a statement about the existence of two integers that were unique. That's another telltale sign you might be looking at something like this. It may or may not be the case, but it's a nice idea maybe to start off. Something to think about. And then once we did that, we used it again, and we simplified. And then we just looked at what the definition means for something to be divisible. Piece of cake, right? So are there any questions about that example there? I think that was pretty cute, because notice that it isn't just simply, oh, I just used the pigeonhole principle. It doesn't say that, right? It requires very specific conditions for me to use it in this example. Are there any questions? Any questions? Don't be shy. And yes, Miss Kitty is okay. I think she's off heading, I'd seen her run off. So we've seen some examples of how using the pigeonhole principle, we can look at large groups. We can look at, for example, applying to a number theoretic claim about divisibility. Pigeonhole principle can pop up at all sorts of places, as I mentioned previously. You could use it, one classic example of using the pigeonhole principle, and I would show it to you today, but it requires a lot of setup for it to work. Usually like a lecture or two of formal language theory to really digest and appreciate it. Well, particular of automata theory. But there's this thing called the pumping lemma for regular languages. The proof for that uses actually it uses the pigeonhole principle. It's a very classic application of the pigeonhole principle from theoretical computer science. It essentially says that there's this way that you can always identify a state. And the pigeonhole principle shows that, hey, look, there's enough states for me to always identify at least one of them, such that you can break it into 3 consecutive parts, such that when you move, you can repeatedly pump one part of the processes of your state machine. But yeah, that's a whole other thing to talk about. It requires a lot of setup. if people are curious about that one day, I can happily do it. It's an interesting subject. It's a question about, hey, look, if I have a model of computation that has no memory, other than the entire thing is stored finite size, it's not allowed to remember stuff, it just knows its state and where it needs to transition to. It's a very basic kind of state machine, what people call finite state machine. It's a question about, it characterizes what we call a regular language. If you ever heard of regular expressions, for example, this is actually closely related to that. Is the existence or non-existence of languages, of machines that could accept a given language that would fall under what we call the regular languages. It's one of the more simpler kinds of languages that express certain kind of languages which correspond to problems we can solve. It's a rabbit hole that's really enjoying. There will be a point where I will go through this, and it's a very fascinating subject in its own right. I'm just going to grab another marker here. Just give me one moment. Okay. So I thought I would show you another example. Before we get to kind of a more theoretic example, I thought I would show you something a little bit different. Something that it's a little bit unclear how you decide what the objects in bins are. I want to show you an example like this. So previously I showed you a number theoretic example for applying the pigeonhole principle. I thought I would show you something of the similar vein, but it's a little bit simpler of a claim. It's much simpler. However, the way you identify the objects in the bins, it isn't quite as clear how you do that. So I thought I would show you an example, and I'm going to call it Lucky 7. Because I'm feeling lucky. So suppose we are given a set of numbers. And it's going to be this set. A is going to be equal to the following. It's going to have elements 1, 2, 3, 4, 5, 6. It's going to have these elements in it. So I have a question for you. Can we pick 4 of the numbers? 4 of the numbers let's go 4. 4 of the numbers in A such that 2 of the numbers add to exactly 7. So imagine this is like you're sitting there being a game show designer. Maybe you're making some game, and you have this set of numbers, and you would like to be able to have it so that if somebody picks 4 of the numbers, I'm thinking of something like The Price is Right or something like that, and you want to set up a game so that you can maybe rig it against the player. I'm not quite sure, but anyways. The point is that suppose I give you that set A. I want to know if you could pick if you pick any 4 of the numbers. So if I pick any 4 of the numbers from A, can I guarantee that 2 of the numbers add exactly to 7? So this is a pretty interesting statement because it's talking about adding numbers. 2, it's talking about any 4 of the numbers in A, right? It isn't just all of them, right? It's any 4 of the numbers. So I thought I would show you something akin to this, so that way you get a flavor for how you might identify the objects in the bins, because here it's not quite as clear what you would do. Because remember, the first thing is that it isn't the whole set A that we're playing around with anymore. Now the statement is about if we pick 4 of the numbers in A. So it could be any 4 of them. So I want us to think about how we could characterize this. So I have an idea. How can we add the 7? So how can we add the 7? In particular, using 2 numbers. So there's something neat about this set. So it's something special about that set over there. Let me show you. So how can we add to exactly 7? Well, you could do 1 plus 6, right? That equals 7. You got 2 plus 5, right? That's equals the 7. You also have 3 plus 4. That equals 7, right? So there's something nice about this is that there do exist ways that you can pick the pairs such that they add to 7. But there's something very special about the way that these possibilities live, because these are all the possible ways that I could add to 7. Now, keep in mind, I'm not counting the ways that you could swap these, but the point stands. Is there something very special about this? Is that the list of ways I can add to it, they form pairs, right? They're pairs of numbers that you could pick. But they're not just that. They're not just that. Notice that if I actually look at all of these elements, they appear exactly once in here. Do you see that? So I have a suggestion for how we're going to set up the objects in bins. So the objects are any 4 numbers of A. So you could give these names if you like. You could call them like A1, A2, A3, and A4. How about the bins? Now that's the part that's a little bit of a head scratcher here. Now, what does it mean? What does it mean for it to be that 2 of the numbers add to exactly 7? That means that if I give you, so I pick 4 numbers out of A. That means that 2 of them have to sum to 7, right? So you gotta look at it a little bit different than we've done previously. Previously, we always had it where, oh, this has a property with this thing. And it's just really direct like that. Really simple. Now, keep in mind, it is still the case like that here. It's just a little bit more subtle. So the bins are going to be the 3 subsets. 1, 6. 2, 5. And 3, 4. Now, these 3 subsets have a special property that they do what we call in set theory, they partition the set A. Meaning that if you take all of these, you put them all together, you get A. But also note that every single one of them, they have no common elements amongst each other. So this is kind of neat because now that means that regardless of which numbers you pick, one of them is going to sit in one of these buckets. That's why we need that. That's why this is a really neat property here. At least for our example, this is why we need it. So let me just kind of draw a picture for you. Just to kind of lay this all out for you. So I have 4 numbers. Say A1, A2, A3, A4. These are my numbers chosen. These are the objects. And then I'm going to have my partition of A. There's 3 subsets. Those correspond to my 3 possible ways I can add to exactly 7 using 2 elements. And here's the catch. Now, I'm hoping that this will connect all the dots for you. is now the relationship that we had was, as I said, each one of these numbers will be in one of these, right? So a very simple way of associating each object with a bin. So this is the partition of A. Each pair adds to 7. These are our bins. So we could define the relationship like this. S of AI this is going to be corresponding to the subset number AI belongs to. So it means that when you pick a number, like you pick the 4 numbers, each one of these sits in one of these. It has to. Remember, these 3 subsets partition A. So it has to be in one of them. And we're saying each one of these gets picked. I want to know if 2 of them add to 7. But now look at this. I have 4 numbers. I have 3 subsets. What can you guarantee is going to happen? There's going to be at least one of the subsets where these numbers are going to appear. But there's going to be 2 of them. And those are your 2 numbers as I had in my question, right? So the way we're using the pigeonhole principle is a little different here. What we're doing is we're allowing us to see if these 2 numbers added to exactly 7. What we're doing is we're guaranteeing that each one of those sits in one of these. And since each one of them adds to a 7, when I add the numbers in these, when I apply the pigeonhole principle, what it actually does is it's telling me for sure that 2 of them, at least, meaning when I pick 2 of them, they're going to add to 7. And keep in mind that because of the way I have to pick the numbers, they have to. It has to be 2, okay? So let's put this all together now. So yes. By the pigeonhole principle, at least 2 numbers. In fact, if they're all distinct, but anyways, let's keep going here. At least two numbers from the 4 occur in one of the 3 subsets. Now, I have a question for you. If I were to change this question a little bit, instead of it being 4, how about 3? Can we use the pigeonhole principle like we did here? No, we can't do that, no. Why? Because, for example, it's possible for me to pick, say, 1, 2, and 3. Those are 3 numbers I could potentially pick, right? Out of the 3 numbers. Notice that regardless of which way you pair them, none of them add to 7. Do you see that? So this is one way we can use the pigeonhole principle when we want to characterize sums. The whole trick here is to notice that we have partitioned the set such that when we have all of the elements here, these are all the possible ways we can add to 7, and these numbers have to occur in one of these subsets, exactly one of them. So, very careful application of the pigeonhole principle here, but a kind of cute one too, at least for additive properties. Are there any questions about this one here? Any questions at all before we get to one of our more involved examples? Because we got some more stuff we're doing. We've got, but are there any questions about this one here? Or any questions just generally before we proceed? Because we're going next to party time. Because I want to show you how you can use the pigeonhole principle to argue in at least a couple different ways. I'm just looking ahead what we got going on. Yes. Any questions at all? Don't be shy. Anybody's welcome to ask questions. Everybody's welcome. If we're okay with this question, let's, this problem, let's consider I want to consider something that's I would argue is a pretty classic example of using the pigeonhole principle, but it pertains to graph theory. But I'm not going to characterize it as a graph theoretic result for now. And then I'll show you where it pops up with graph theory. And what it means in terms of graph theory. Okay. So I thought it would take a little bit of a breather with a different kind of example here. Now, I'm going to characterize this graph theoretic claim in terms of having a party, okay? So I'm going to call this party time. Party time. Excellent. So suppose you are hosting a party with n greater or equal to 2 people. We're going to have 2 or more. That includes yourself as well. There's 2 or more people at this party. Now, people at a party may be friends or they may not be friends. But the point I'm getting at is that, and this is going to be actually an important nuanced point here, is that we are going to define that friends are mutual. So people are either mutual friends or they're not. So for example, if Miss Kitty's having a rough day and she doesn't want to be friends with me, that doesn't count as being my friend because it's not reciprocal. It's not mutual. Okay? Now keep in mind that Miss Kitty's still my friend, but I'm trying to be a bit playful with this, okay? So people at the party so when I say be friends, I'm talking mutual friends. Mutual friends or not. Now, this is where it's going to get a little bit weird, especially if you've never seen this before. Here's my claim. Here's the claim. Some pair of people at the party are friends with the same number of people at the party. So let me just state this again. Some pair of people at the party are friends with the same number of people at the party. So that means that there's going to be 2 people that if you asked everybody at the party who's friends with who, and you tally up how many friends they have, there's going to be 2 people that are going to give you the exact same count. That's what the statement says. It doesn't say that they're the same set of friends, just to be very clear. It's just that the number of friends between these 2 people are the same. So, I want to give you an example of how we could prove this claim in a couple different ways. So, this is mainly to illustrate for you that you could use the pigeonhole principle in a couple different ways. We've seen an example where we directly use the pigeonhole principle. So, I'm going to start off first by proving it directly, this claim, and then I'm going to prove it using contradiction, just to show you. And I'm hoping the first time you go through, you'll get some ideas of how we would go about proving this. Then the contradiction proof will go a lot smoother. Smooth like a banana peel on a wax floor. So we're gonna actually present 2 proofs here. So proof 1 is going to be based on a direct argument. That means we're just going to use the pigeonhole principle. But the form of the, well, actually, in both cases, we're going to use the pigeonhole principle. What it means is that the way I'm going to argue this is I'm just going to start just right from the case. I'm just going to use what I'm given, and I'm going to break it into cases. For example, example of a direct proof would be breaking via cases. And I'm just going to work my way that way. I'm not going to use any fancy logic tricks on you. No fun magic today, okay? Magic. So anyways. So here's where we're going to start. We're going to examine the numbers of friends. The numbers of friends a person can have at the party. Seems like a pretty sensible place to start, as we just find out how many friends can a person have at the party, right? So let's just see what that's about. The number of friends a person has at the party is at least what? Can somebody be at the party and not be friends with anybody? Technically, by our way characterizing being at a party, yeah, somebody could be at a party with no friends there. There could be somebody with no friends at all at that party. Maybe they just got an invite from somebody and they just showed up, but they weren't friends with anybody. Just some random schmo that showed up. At least 0. And at most what? Now, notice that I said mutual friends. You can't be mutual friends with yourself, okay? You're friends with you could be mutual friends with somebody else. So there, you could have at most n-1 friends if there's n people at the party, right? So it's something between these 2. Now, depending on this fact, so now we know that every person can have at least 0 friends and at most n-1 friends. We're going to break this into 2 possible cases depending on how our party is configured. So, for example, is there a friend that has 0 friends? Sorry, is there a person at the party with 0 friends? That may or may change how we might go about this. So let's watch what happens. So there are 2 possibilities. So we're going to break it into cases. So it's technically a proof via cases. There are 2 possibilities. So using the information we just absorbed here, absorbing it like energy from the sun, like Sunny D or something. Just suck it in my veins. So there's 2 possibilities. So as I've already told you, there is a possibility that somebody at the party has 0 friends. So case 1, a person has 0 friends. If they have 0 friends, I have a question for you. If there's n people at the party and somebody has no friends, can there be somebody with n-1 friends? Like, say Miss Kitty. Miss Kitty shows up at the party, nobody's friends with Miss Kitty, because Miss Kitty's being a bit of a being something. Maybe everybody was just a little upset with Miss Kitty that day. But still they're their friend, but you get my point. Is that, suppose that just for the fun of it, that nobody's friends with Miss Kitty that day. She's coming in trashing your boxes. But if that's the case, can anybody have n-1 friends? No, nobody can. Nobody can in that case. Because you would have to be friends with Miss Kitty. You would have to be if you have n-1 friends. But that person has no friends at all. Then, no person can have n-1 friends. Can have n-1 friends at the party. So what does that mean for the number of possible friends that somebody can have then is? Well, we've definitely constricted it. It can't be, in this case it can be 0, but it can't be n-1, right? So the possible number of them, it may be some subset of this in reality, but most certainly it cannot be, what does it mean? The numbers of possible friends a person has is 0, 1, 2, all the way up to n-. Is it n-1 or is it n-2? It's n-2. You can't have it be n-1. So just to reiterate, a person has 0 friends. In that case, no person could have n-1 friends at the party. The numbers of possible friends a person has is 0, 1, 2, all the way up to n-2. But not n-1. Not n-1 at all. You can't have n-1 friends in that scenario. Otherwise, every person has at least one friend. Right? That's the only other possibility out of these two. You can exhaust this to more cases, but this is everything else but that. Every person has at least one friend. So in this case, then the numbers of friends that people can have, it doesn't include 0, right? That just seems rather straightforward, right? The numbers of possible friends a person has at the party belongs to, give me a drum roll. It's gonna be in this set. 1, 2, 3, all the way up to n-1. Well, what can you observe about both cases? How many elements are in both of these sets? n-1 many elements. How many people are at the party? And so let's use that fact. Regardless, the numbers of possible friends a person has at the party time, at the party is less than the number of people at the party. At the party. Now, this is where we pull out our friend, the pigeonhole principle. Here we go. Therefore, by the pigeonhole principle, some pair of people are friends with the same number of people at the party. That completes the proof. So, if ever you're at a party and you're looking for something to brag at somebody, pull out. My friend Dre would be lovely for this. Get himself a notebook, start making a tally of how many friends are at the party, and my friend Dre could come up to you and tell you, "Hey, look, there's going to be 2 people that are going to have the same number of friends at the party." I didn't have to write it down, but I could tell you who they are. So that's what we could say for the pigeonhole principle in this case. So that's the direct proof. There's the key things I really want you to observe is how we use the fact that we could actually restrict the number of possible friends that somebody can have at the party. In this case, we exhausted those possibilities. In this next version of this proof, we're going to be able to do a little bit less work, but it'll be enough to prove the claim. So let me just back up over here and we're going to see the second proof. And then once we've done that, I'm going to show you how this actually connects quite nicely with graph theory. Because what we've actually been talking about is actually a graph theoretic statement. I just haven't really spelled it out to you yet. In fact, if you were to prove this with in graph theoretic terms, the proof will go very similar to this. You just put in graph theoretic terms. So let me show you a different proof. This one's going to use contradiction. So for those that are just like, oh Dan, let's get to the graph theory. Feel free to, if you're watching this in the future, feel free to pass what we're doing. But right now we're doing this all together. But I think there's something to appreciate about the contradiction version of this proof. So let me show you how we could go about this using much of the same ideas we did before. So here's the game plan. I'm going to assume otherwise. So that means that, what does that mean about this statement then? If it says there's some pair for which they have equal numbers of friends at the party, that means that no friend has equal numbers of friends at the party. Sorry, no person at the party has equal numbers of friends. So we're going to use that fact and it'll come out quite nicely. So that's the game plan. Assume otherwise. So assume otherwise, then no pair of people at the party at the party have the same number of friends. But what does that mean? If they don't have equal numbers at all, that means that every single one of the people at the party, if I ask them how many friends they got, all of them are going to give me a unique number, right? That's what it means. This implies that every person at the party has a different number of friends at the party. So that means that all of them have a distinct number. But what did we say before? That we can actually characterize how many friends somebody can have at the party, right? We're going to do the same trick. Then, the number of friends a person at the party can have is in this following set. 0, 1, 2, all the way up to n minus 1. For each value, now because remember there's n people at this party and there's n things here, right? So that means that each one of my friends at the party has to take on one of these numbers, right? I don't know who takes on what number, but there's only n of them there, right? Because 0 up to n minus 1, that's n of them, right? So that means I can't just simply say, oh, some of them might have the same one, because we already assumed that that isn't the case, right? For each value in this set, there is a person at the party, right? Now, we pull out our trusty trickery that we had last time. Now, it doesn't matter which version of this you would like to do, but the main thing I need to point at is that we could pull out our scenario where we had with Miss Kitty. So what did we say earlier about Miss Kitty? Miss Kitty's got no friends at the party. People are upset with Miss Kitty. She knocked their box over. But suppose that you're maybe a really great host and you're friends with everybody at the party. So let's flip this around just to be a little bit positive about the whole scenario. Since one person must have n minus 1 friends, right? Somebody has to, because that's one of the numbers in there. No person has 0 friends. Miss Kitty, you're out of here. Hoo-yah. So, sorry, that wasn't Miss Kitty. That was just me kicking air. Sorry, I'm having a little bit of fun with this. So the number of friends a person has are, I'll say is in 1, 2, 3, all the way up to n minus 1. It's got to be in this set, because We know one of them has n-1 friends, so somebody can't have 0 friends. It's not possible. Since there are n people and the numbers of friends a person can have at the party is n-1. Now this is where we get pulled at the pigeonhole principle. By the pigeonhole principle. By the pigeonhole principle. At least 2 people have the same number of friends. But what does that mean? It's a contradiction, right? Because we assume that so it has to be, because this is a contradictory statement, because we assume that no pair of people have the same number of friends. But by the pigeonhole principle, we said that now we're also saying that there are at least 2 people that have the same number of friends, which is a contradiction. You can't have both those 2 things be true at the same time. It's impossible. That marks the end of the proof. So this is how you could use the pigeonhole principle in the context of a contradiction proof. So notice that it doesn't change the nature of how the theorem gets used. It's just that the setup for how you get the argument to work, you mostly want to get it propped up so that the pigeonhole principle often is the thing that gets you the contradiction. So just use it very carefully if you're planning to use it like this. You'll find that many of the ideas we had actually came out of the first attempt we had. But either way, it's just something to think about. Now, I promised you I was going to show you how this connects up with something from graph theory. So let's talk about that now. Okay, so here's an application for graph theory. So actually everything I've talked about actually has an equivalency with the statement in graph theory. But let me just give you an idea of what I'm talking about. Suppose that there, for example, were 4 people at a party. I'm going to represent these as vertices in a graph. You can just think of them as dots that represent the people, if that makes it easier. So suppose there's 2, 3, 4. Now, suppose person 1 is Miss Kitty, and we established Miss Kitty's got no friends. How about person 2? Person 2 maybe is friends with person 4, and person 3 is maybe friends with person 4. So, notice that actually the relationships that I describe in the party actually are characterized by an undirected graph like this, because the friendships are mutual. So we're characterizing mutual friendships when we talk about our friendships here. So notice that there exists what we call an edge, whose endpoints are friends, that represented by vertices, if they are mutual friends. If there is no edge, for example, from 3, 1, that means that friends 1 and 3 are not friends, mutual friends with each other. So notice that actually what we've been talking about is actually a graph theoretic statement. So let me put this all into context here. So, in short, we've been talking about undirected graphs. So vertices are the people at the party. And the edges, these are these lines that, or connections between the vertices. Edges represent mutual friendships. As we discussed previously. Now, let me put this into fun graph theoretic terms, okay? So, we have this concept, and I've talked about this before, called the degree of a vertex. So, this is simply the number of edges. And here comes a word that I'm just going to parse quickly for you. Incident on a vertex V. So we'll write this as dag of V like this. So this is the degree of a vertex. So what does it mean for edges to be incident on a vertex? So all you're doing is you're looking at the sticks, these edges that connect, that go out from that vertex. So for example, vertex 4 has degree, so the degree of vertex 4 is 2. The degree of vertex 1 is 0. Notice there's no edges going out. You count the number of edges that go out. The degree of 2 is equal to 1, right? It just says one friend at the party. And the degree of 3 is 1, right? So, believe it or not, if you actually think about what we've just been doing all this time, this is actually a statement about the degrees of vertices in a graph. So, we have the we have the following equivalent theorem. So you could take the proofs that we've given previously, regardless which form you would like them, just change them into graph theoretic terms. You have the exact same argument though. Is this one. So given a simple, now simple just simply means that you obviously can't be friends with somebody more than once, and you can't be mutual friends with yourself, right? So given that, so in a graph that just simply means you can't have what we call parallel or multi-edges, and you can't have self-loops. But I have no doubt that there's easy ways to get around some of these things, in some sense. But we're just going to talk about this more fundamentally. So here's the equivalent theorem here. So given a simple undirected, just simply means that the edges, there's no assignment of a direction on the edges. It just means that you can go from 4 to 3 to 3 to 4. It doesn't matter. It just represents a connection between these two endpoints of an edge, 3 and 4. Given a simple undirected graph with at least 2 vertices, there are at least 2 vertices with the same degree. So this is a statement about simple undirected graphs, or just some people just call them graphs. It says that if you have at least 2 vertices, think of it as 2 people in the party, at least 2. What you could say is that there's always going to be at least 2 vertices, those are those dots over there that we've numbered. They're going to have the same degree. The number of incident edges are going to be the same for at least 2 vertices. Try as you might, you won't be able to come up with a graph where all of the vertices have distinct degrees. So that's an interesting connection between having a party with your mutual friends, or some people, some of them are mutual friends, and graph theory. Pretty neat stuff, right? And the way we could prove this quite nicely is using the pigeonhole principle. So are there any questions? Any questions at all? So that's my last example for the pigeonhole principle. What we're going to do next, and I'm looking at the time because I'm like, well, I could keep going because I actually have more. I got a bit more. It'll amount to about 3 more kind of segments. So maybe for another hour. Hour at most, hopefully. But I want to talk about the averaging principle because I promised I was going to talk about the pigeonhole principle and then the averaging principle. So I think the next thing we'll do is we'll talk about the averaging principle. We're going to do an example. Oh wait, no, we're not at the averaging principle yet. I still have to talk about the generalized pigeonhole principle. Let's get to the generalized pigeonhole principle next. We're going to talk about that. And then we'll talk about the averaging principle. And we'll see how much time we've got. So if you're enjoying this, please let me know. We're having ourselves a good time here. Miss Kitty causing chaos for everybody. I'm just erasing the boards. That way we could get to our example. So previously we talked about the pigeonhole principle. It gave us a guarantee of 2 or more in a bin, right? Well, what if I told you we could generalize this idea even further to try to make that bound a little bit better? So for example, if I have many objects and not as many bins, I want to know if there's a bin that has at least some number of objects that is going to be hopefully higher than 2, a much closer idea of how many must be in at least one bin than just 2. So that's what we're going to talk about next, is the generalization of the pigeonhole principle. So are there any questions? I'm going to drink a little bit of water here. I'm working on my ankle here, so it's a little bit... We're going on quite a bit of gas here. Not like literal gas, not flatulence. I just mean mostly because I'm still recovering a little bit. Okay. Now let me just... Okay. Now here's the cool part of what we're going to talk about next. Is the arguments we're going to use are going to be extremely similar to the ones we had for the original pigeonhole principle, except they'll feel like even easier because you're used to the arguments because we've used them at least once. And then we'll see an example, and then we'll talk about the averaging principle, which is a lesser known counting principle, but it's very much, if you talk about integers, it's equivalent to the averaging principle. And so the pigeonhole principle and the averaging principle are equivalent to each other. They're different formulations of the same idea. If you only are presuming discrete objects. So the averaging principle is a generalization of that idea. So anyways, let's talk about the generalized pigeonhole principle. So up to this point, we've talked about the pigeonhole principle, and we are able to guarantee that there's some bin that has at least 2 objects. Now, if I have many objects, it may be the case that there's actually some bin that has more objects than just 2. So there's actually a generalization of the pigeonhole principle that we can actually easily prove using the same techniques we did for the original pigeonhole principle. So this is one generalization of that. So let's state it, and we're going to prove it. Then we'll see an example. So I'm going to refer to this as the generalized pigeonhole principle. So I'm going to let n be a positive integer, just to make this a little easier to play around with. So this is the set of all integers. But I'm adding the plus just to say, hey, look, it's all the positive integers. So it's 1 and above. So suppose n objects are put into into M bins. And I must stress that it's the case that M is when N is strictly bigger than M. Then at least one bin contains at least the floor of n minus 1 over m. This is stripping away the fractional part. So for example, if I have a number like 2.5, the floor of 2.5 is 2. You just strip off the fractional part. You just keep the integer part. So that's what this symbol here, it's the floor function, or floor, is at least this. And in particular, this is actually, I should mention that this is actually equivalent to me writing this. What we call the ceiling of n over m. So the ceiling is where you always round up the fractional part to the next integer. So for example, if I have 2.5, the ceiling of 2.5 is 3. Likewise, the ceiling of 2.9 is 3, and the ceiling of 2.001 is also 3. But 2, the ceiling of 2 is 2. Is at least the ceiling of n over m objects. Now, I'm not going to prove this equivalency here, but this is true because these are both positive integers. Now, let's prove this. And you're going to find that this proof is really, really cute. It's honestly a much easier proof than taking and picking up its functional counterpart. We talked actually, when we talked about the pigeonhole principle, we talked also about how it connects to functions. Now, the proof there requires you to phrase out and formalize a lot about functions. Here, when we just think about objects and bins, it's actually rather nice, and the argument's quite similar. So, we're going to assume otherwise, for the sake of a contradiction. Well, let's think about that. What does it mean for this statement to not be true? Well, it means that there's going to be no bin that has this property, right? But what does that mean? That means that every bin has, at most, that many objects minus 1, right? So, thus, similar to the way we also argued this for the pigeonhole principle originally, we had at most 1 per bin. Now we're going to have at most this minus 1 per bin. Thus, the total number of objects is at most, well, we're going to have for each bin, you're going to have n minus 1 over m with the floor, like this. Remember, it's just 1 less, right? Because if you did, then they would satisfy this condition, right? But this is less than or equal to m times whatever this would be without rounding it down, right? This either has to be the same as that or it's bigger, right? But let's see, m times this over m divided by m, you can just cancel those out, you end up with n minus 1. But this is strictly less than n, right? That means that the number of objects isn't actually equal to the number of objects. In fact, it's less than that. So the bin actually contains less objects than there actually are objects. There just isn't enough room. So, which is a contradiction. Piece of cake, right? So there's a little bit more setup in there that I sort of omitted just because you've seen the original proof. But the main argument is sitting right in front of you. So hopefully that is clear. So I'm going to do an example where we apply the generalized pigeonhole principle. But the big thing I really want you to just to see it in the back of your mind is that this, when you rewrite this actually looks like something. It looks like the average, right? That's going to come up when we start talking about the averaging principle. So just keep that in the back of your mind. Just like take that idea, just put it behind your ear, and we'll talk about that in a bit. Okay? So let's consider this example. So we're going to do a very simple application of the generalized pigeonhole principle, because this is very often how you might use it, at least on quick offhand. So given a group of 85 people, do at least 4 have the same first letter for their family name. So you'd agree with me that at least if we're writing English, the first letter of a name would be an English alphabet letter, right? It'll be one of the 26 letters. So if I give you any one of these people, when I look at their family name or last name, it will have a first letter. And it must be one of the 26 letters in the English alphabet. So, well, let's do the same thing we did with the pigeonhole principle. We identify the objects and the bins. And because of the way here, it's very natural. So here's the objects. So what are the objects? So the people, each with a family name. And we have the bins. There are 26 letters in the alphabet. So now all you have to do is you associate each family name with its first letter, right? So now let's use the generalized pigeonhole principle. So notice that 85, it's bigger than 26, and that makes sure that we have it where when we calculate this guy over here, that we're going to ensure that something's going to come out of this nicely. So I do want to make a note here that I do see that the way I wrote the generalized pigeonhole principle doesn't require that m is strictly bigger than n. Sorry, n is strictly bigger than m. This is because when n is strictly less than m, you can guarantee that the floor part is 0, so you end up with 1. So it means, and since you have positive number of objects, one bin's going to have 1 in it at least. But that's just a remark. So let's apply. So with applying, that's just a remark. Applying the generalized pigeonhole principle, the floor of 85 minus 1 over 26 plus 1. Now this right here is 84 over 26. Now if you take that and you try to play around with this, well, that's already going to be bigger than 3 times 26, but it's not bigger than 4 times 26. So you're going to end up with this being 3 plus 1, which is equal to 4. So there's going to be 4 objects are in some bin. But what does that mean? That means that there is going to be, for my group of 85 people, each one with their own family name, there's going to be at least 4 of these people that are going to share the same first letter for their family name. So the answer is yes. Now, something I'll get you to think about. Please let me know what you think about this one. And if you're watching this in the future, feel free to put it in the comments if somebody doesn't answer it here. But this is more of an exercise for you to think about. Is suppose that I gave you 79 people. Or say 75, actually okay, 79, 78, 77, I'm just trying to think off the top of my head here. How many people, what's the smallest you can have for a group of people such that you guarantee this property? So it should be somewhere around the high 70s for this property, where if you imagine you try to make that group as small as possible such that you could at least 4 have the same first letter for their family name. I want you to think about what would be the smallest number you would require. It should be something in the high 70s. So the point I'm getting at is that the generalized pigeonhole principle is very applicable when you want to know if there's some bin that has at least some number, but it's better than just saying there's at least 2. Okay? So are there any questions? Any questions at all? So that's the generalized pigeonhole principle. I find that it's really intuitive because if you actually think about it, like I said, it's like getting the average. And yes, I am thinking off the top of my head to myself, yeah, it is the case that you don't require that n is bigger than m. And let me just show you that, just to be clear, because suppose that the number of bins exceeds n, and remember, n is still a positive integer, right? So that means that n minus 1 over m plus 1, like this, is, if this is the case, that means that this number, whatever this is always going to be less than m. In fact, actually, if you make it so it's like this is guaranteed now to be 0. So if m were greater or equal to n, this would be 0. But remember, there's still a positive number of objects. So it is going to be the case that it's going to have it where some bin is going to have 1, which is correct. It is correct. I don't know. In my notes, I said that for some reason in my notes, I didn't actually have that quantifier right there. So I kind of think it's silly that I decided to add it in. But I mean, it's still a true statement, but it's most certainly not as versatile as it actually is. So if you've got your notes, please just you don't need to include this when n is bigger than m. You shouldn't need that for this proof to work. Well, sorry, the generalized pigeonhole principle to work. Just part of my inclination of saying, hey, it's a generalization. But it's just one way of generalizing it, because I mean, the main application of this version is just to say, oh, there's some bin with at least some number. Its purpose isn't really to say, hey, look, it's saying something about a bijection. This one's more about objects and bins. At least in that version of way of looking at it. Okay. So please, if you have any questions or any comments or anything, let me know. So next, we're going to talk about the averaging principle, as I promised. Now, I'm just going to see what I got for markers here, because my markers are a little bit spotty. Okay. So next, what we're going to do is we're going to talk about so this is the last thing we're going to talk about here today. I'm going to give you, actually, there's going to be kind of like 3 chunks to this part. Namely, there's going to be the averaging principle, how I derive it from the pigeonhole principle, in particular the generalized pigeonhole principle. And then I'm going to show you how you prove the averaging principle. And then we're going to see an application of it for scheduling. and then we're going to prove a claim using the averaging principle. So let me just get things sorted out here. I got cats all over the place here. Somebody save me. Let me see here. Averaging principle. I like I said, I just got cats all over my table. There's this. Okay. Yeah. Okay, 92. Yeah, there we go. I'm just gonna put aside the rest here because we don't need any of this stuff. I'm bringing out some blocks. Okay. So, since there aren't any questions, let's proceed. So, up to this point, we've talked about the pigeonhole principle. We talked about the generalized pigeonhole principle. Now, I want to show you a reformulation that generalizes over the generalized pigeonhole principle. It's called the averaging principle. Some people like to think of this as a precursor or prototype for the probabilistic method. So if you've ever heard of that before, this is going to feel like kind of like a baby step towards that. So we're going to consider a reformulation. So I want to show you just to convince you of the averaging principle for integers. So if I have an integer number of objects, an integer number of bins, I would like to show you where and how we can get something that's going to approximate the averaging principle more broadly. So I want to just show you how we could take the generalized pigeonhole principle, turn it into what we're going to see is called the averaging principle. So consider a reformulation of our previous counting concepts from the pigeonhole. Now, suppose that we're given a non-empty, so that means that we have at least one element in it. It's non-empty and finite. Finite collection. So that means that you're allowed to have duplicates in here. That's just why I'm using the word collection as opposed to a set, but it's still true for a set too. A collection A of n numbers. So I'm using the word numbers here more explicitly. So here's sort of a broader conceptual question. Is there an element in A that is at least some number we're going to call mu? Now, it's a little bit of a hint where we're going with this. If you see the word average and you hear see a symbol like mu, you might know where we're going with this. But and I must stress that which may depend on A. So it's not just a constant or something. It's going to be something you could calculate based on A. So I want to try to see if we could figure out what mu might be. Now, so notice that this is slightly different in the way I formulated it. Now it's a collection of numbers, and I would like to know if there's some number in that collection that is at least something called mu. So let's try to determine mu in the special case when A has positive integers. So let's just work with positive integers. We assume that those numbers are positive integers for now. So we're going to do something kind of crafty here, so pay attention very closely. So for example here, suppose that I give you a collection like this. 3, 2, and 5. Some people call that a tuple. So it's a 3 tuple. It has 3 numbers in it. These are all positive integers. And I'm going to try to come up with a way to figure out that there's some number at least that depends on A. So there's going to be something in here that I could guarantee is at least mu. So watch this carefully. I'm going to visualize this a little bit differently than I would otherwise. I'm going to view each position in A as a bin. So, for example, there I have three objects. Sorry, not 3 objects, 3 bins. 1 for each position. I have 3 positions, 3 bins. So I want to view each one of them as a bin. Now, each number A in A itself in the collection as A objects. So example, 3 is 3 objects. So when all of A is considered, when all of A is considered, it totals to the sum over all of the elements in A of their values, many objects. So there's that many objects. And the reason why I'm allowed to do this is because all of them are positive integers. So please keep that in mind. So this whole idea, the way it works, is as long as I can take the numbers and I can break them into discrete sizes, this trick works. So integers, it's rather trivial, because I could just say, oh, the number itself is that. So what I'm trying to say, and let me try to visualize this, is 3 is like having 3 objects. 2 is like having 2 objects. 5 is like having 5 objects. And now these might occupy these bins as a potential placement of where these values could be. If I were like a Skeksis or something, like from the Dark Crystal, I would say this is the essence of the numbers. So what we're going to do is we're going to drain the essence from the numbers by taking all of these and bucketing them all up into one big super bucket. Now, it's not a bucket like these. These are bins. I'm just going to collect up all of the objects. And since this actually adds up to 10, we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 objects in total. And I have 3 bins. So now, how many, so if I look at this in terms of this, now I have 10 objects, 3 bins. If I were to imagine, like of how some Skeksis, I could like take the life force from one and just give it to another, and say one of these bins, like I drained the essence from one of these and I put it in one of these bins. What can I say about there being, like, for one of these bins, for some bin, if I have 3 bins and 10 objects, how many must be at least in some bin? Well, the generalized pigeonhole principle tells us this. It tells us the answer to this question. No, get back here. Get back here. I'm not going to drain your essence. So let's go back over here. So the generalized pigeonhole principle states some bin has at least how many? Well, remember, how many objects did we have? We have the sum over all of the numbers in the collection has at least this many, right? So that's how many objects I have. This is how many bins I have. It has that many objects in it. That's what the generalized pigeonhole principle would tell you. So, now this is where it gets a little bit weird, because now we got to translate this back to our original question. So remember, the bins represent the positions the numbers can occupy. So now, when we think about a bin, we're actually thinking about the number that might be sitting there. And the number of objects is its value. So translating this back, there is a number in A, remember, that's among all of the bins, because there are 3 bins, one for each position. Those are the positions in A. That is at least what we have above. But this is the ceiling of this, right? You would agree with me, I could just drop the ceiling and the value either stays the same or it gets smaller, right? So I'm just going to write it like this to make it a little easier for us to parse what's going on. And I'm saying that this value here, this is mu. But what's that? That's literally the average. That is literally the average. So this brings us to this is the average, right? This is the average of A. So remember, the argument that we've employed to derive this argument here, this relies on the fact that they're positive integers. You could actually prove a statement that's far more general using the same kind of techniques we've actually used for the pigeonhole principle, and this will work even for real numbers. So if I give you n positions in my collection, and the numbers are real numbers, then I could still prove that actually there's going to be some element or some number in the collection that's going to be at least the average. And it must be this guy. Likewise, you could actually prove also another fact, and this is what makes it sort of a neat concept other than just the pigeonhole principle, is that there's also an element that is at most the average. So there's 2 parts to it. The proof is actually surprisingly simple once you've seen how you can prove like the generalized pigeonhole principle, because they're based on very similar ideas, just we need to make sure when we prove the claim, we don't make any assumptions that they're integers. So let's state the averaging principle, and let's prove this. So we've seen how we could get the averaging principle, for at least one part of the averaging principle, for positive integers, but we're going to prove this more generally, okay? So this is actually neat in its own regard because now it actually gives us something to say. If no matter how the numbers are, like remember, this is a statement about numbers in a collection. So I'm hoping I can give you an intuitive idea, if you're not familiar so much with statistics, why this has some interesting feature to it. And for some of you that have some experience with statistics, this will feel very obvious to you. But we must not get into the land of just presuming, just because it looks obvious, it must be true. It's a big mathematical mistake. A trivial statement merits that. This is something that's a little bit more, this is something it's more than just saying 1 + 1 = 2, okay? This is something a little bit more specific. So, theorem. So this is what we're going to refer to as the averaging principle. So given a non-empty and finite collection A of n numbers. My proof will presume that they're real numbers, but you'll find that the arguments, as long as you're, this should be fine enough for us. Of n real numbers, the average of A is mu, which is going to be equal to 1/n times the sum over all of the elements in A of A. So here's what the real heart of the averaging principle is about. There exists number x in A that is at least mu, and there is a number y in A that is at most u. At most mu. I must stress as an important note that x could be equal to y. So x and y can be the same. For example, if your collection has all the same elements in every single one of the spots, like all the elements are all ones, then what the averaging principle would say is that, oh yeah, well, the average is 1. That means that x, there is an element that is at least this, and at most that, it's namely 1, for example. So let's prove this. So let's do a proof together. So we're going to prove it in two parts because there are two parts to this theorem. The first one is that this part about the saying that there's an element that is at least mu, and then there's an element that is at most mu. Those are two parts, so we're going to prove them separately. You're going to find that the arguments used are very similar to each other, so much so that I actually changed it up, because you could use essentially the same idea in both directions. Well, not directions, but both parts, to be a bit more precise. So my apologies. We prove the two parts of the theorem separately. So the question is, which one should we go for first? I think we're going to go with the at least mu part. I don't know what you think. I think that that's a pretty natural one to start with because that's the first thing I stated here. So first part, First, we prove there is a number that is at least mu. So now we're going to use contradiction because it makes things a little bit fun with us. So I'm going to assume otherwise, then that means something. I want you to think about what that means. So we're going to assume otherwise for the sake of a contradiction. So assume otherwise. So assume or otherwise. So it says that there exists a number that is at least mu. That means that every number has to be what? At most. Or at most? Or is it what? It's less than mu. Right? If it was equal to mu, then it's at least mu. That means that every number has to be less than mu. It must be that every number in A is less than mu. Now, watch this. Just watch. Watch how this works. Then, let's write out the sum of all the numbers. And the sum from over all of the elements in A, all those numbers, you'd agree with me that this has to be strictly less than if I took and replaced each A with mu, right? Because every element is less than mu. But what is this? There are n elements or n numbers in my collection. So I'm adding mu n times. That is the same as me writing n times mu. But what is that? This is n times the average of A. Times 1 over n times the sum of A. Right? That's what mu is. But do you see anything interesting going on here? Look, we got n times 1 over n, right? So we're going to annihilate each other. And we end up with just the sum. This sum, right? Do you see a problem with this? This seems a little nonsensical. Can you see why? What's going on here, guys? Looks a little funky. What did I say over there? That the sum over all the elements in the collection is less than this, right? But we show that that is in fact equal to this. So the sum over all the elements in the collection is less than the sum of all the elements in the collection. That's nonsense, right? Because they have to be equal to each other. Literally the same thing. Which is a contradiction. That's not possible. Now, that brings us to the second part. We're going to use the same strategy. Now, I must stress you don't have to go about this way, but you'll find that this is just as fun. I'm just going to write it like this, just to change it up. Next, we prove that there is an element. There's an element or number. Let's write number, just to be a bit more precise about our language. There is a number that is at most mu. Now, we're going to assume again, for the sake of a contradiction, we're going to assume otherwise. So again, what does that mean? If it's there's going to be some element that's at most mu, that means that if I make that means that if that's not true, that means that every element has to be greater than mu. Assume otherwise, then every number in A is greater than mu. And we can do something quite similar to what we did before. I'm just going to shake it up a little bit. I'm just going to do a little dance. Just shake it up. So mu, the average of A, is just this, right? Right, that's the definition of mu. This has to be strictly bigger than 1 over n times the sum over all the elements in the collection where I replace A with mu, right? That has to be the case because every element in A is strictly bigger than mu. But what's this? Well, that's 1 over n. We add mu n times. This is the same as me writing this. N times mu, because that's just, we're adding mu n times. But what is this? N times 1 over n, that's supposed to cancel, so I just end up with mu. Again, we end up with a nonsensical situation because mu is now greater than mu. That doesn't make any sense because mu, it's saying that mu is equal to mu, but mu is not equal to mu. It doesn't make a whole lot of sense. Like this part is saying mu is not equal to mu, which is a contradiction. And that completes the proof. So that's your proof for the averaging principle. So the averaging principle, just to summarize, it tells you that if you give me a collection of numbers, and so this is a statement about a collection of numbers. So you're allowed to have duplicates in there and everything like that. What it says is that there always will exist an element in the collection that is at least the average of the collection, and there exists an element that is going to be at most the average in the collection. Are there any questions? Any questions at all about the averaging principle? I'm going to show you an interesting example of how we can use the averaging principle in the context of scheduling. And then I'm going to finally wrap things up with an induction proof that checks something in graph theory. I'm pretty sure I got something from graph theory that we can play around with. Let me just see. Just want to make sure. Yep. We got something from graph theory to play around with. So I'm going to try keeping the discussion for the scheduling application a little bit brief, but I'll have more details in the notes. But let me just erase this. So I'm hoping that you'll find this next application neat. I personally think it's one of those things that when you look at it, it's like, okay, that's kind of obvious. Oh yeah, now I'm reminded why I was going to say is that the whole idea here is that you can find two elements, they may be the exact same one, such that you can bound from below and above the average, which is very intuitive for someone to think about. So I'm going to bring that up again when we talk about this application. Sometimes when people see this application, it's like, oh, well, that's kind of obvious. It's like, okay, well, how do you know it's true, though? The averaging principle makes it really easy to justify it. And there's a very clever mechanism that's hiding underneath it. Okay, so there aren't any questions, so let's proceed. So we've talked about the averaging principle. So just to summarize the averaging principle, what it says is I give you a non-empty and finite collection A of n numbers. And it says that you can find me an element in A. So there exists X and Y in A so that if you give me the average, which I'm just going to write as mu, the average of the collection A, you can write it like this. And that's really intuitive if you think about it now. Is that there's going to exist these two elements such that there's one that's going to be at most mu, and there's going to be one that is going to be at least mu. So that is what the averaging principle says. So when you lay it out like this actually makes it's very intuitive. In fact, it's so intuitive that if you had a finite collection of numbers and you laid them out from smallest to largest, it kind of makes sense that the smallest number, there's most certainly going to be a smallest number, and the average wouldn't make a whole lot of sense to be smaller than the smallest number, right? Likewise, you can imagine you have the largest number. Well, the largest number is most certainly going to be larger than this number, right? So you can see that the average, it makes sense that the average would be somewhere in there, right? It won't be somewhere way out there. But the point is that you can say that there exists these integers. You don't have to pick the maximum or the minimum. These just exist. That's the killer, kind of the killer app of the averaging principle. Now, for our application, we're not necessarily going to need to go that full mile, but I like to show this just because it gives you a nice application for scheduling. And this gives you a very easy way of justifying a well-known lower bound on something called a make span. So I thought I would talk about just something before we really get into that. I want to talk about blocks. I'm sure maybe as a kid, possibly, you maybe play with blocks. Now, you have stacking blocks. I only have 3 blocks here. They might vary in size and height. For example, they might be taller, like this purple block might be much taller than just this. So I want to just presume something. So imagine we're going to be stacking blocks. So we're going to imagine we have blocks. Each block has a height. It has a height. And we're going to call that, so we'll call the block BI, and we'll call its height HI. So just for the sake of simplicity, we're not going to presume that there's laws of physics in play for knocking over a tower. An easy way to see how this would work otherwise is just simply just put the tower horizontally on the floor. And then you're okay. So if you want to imagine it like that, go for it. So what I want to do is I want to imagine I have some blocks, like these 3 blocks here. Now in this very special case, I have it where the heights are all the exact same. Now, I want to imagine that when I stack a block, I don't rotate it. It has to go, we only care about the height of the block. It doesn't rotate or orient otherwise. So imagine I stack this block on that one, and maybe I stack this block on this one. Suppose that the height of each one of these is 1, then the height of this tower of blocks is 3. So what I want to do is think about having piles or potential towers of blocks. So imagine that I have, so imagine we have P towers. T, T1, T2, TP of blocks. So there's going to be, so there might be no blocks in it, there might be some blocks. So I'd like to know something. I'd like to know how tall, at least, can the tallest tower be? And also, it would be nice to know also how short, at most, can the shortest tower be. Now, if you're clever, you may notice that I am just framing the averaging principle in a somewhat different way. But here's a clever catch with this. There's something else going on here that's a little bit interesting about how when you stack blocks like this, because keep in mind that each tower has its own height. So each tower has a height we're going to call Tj. We'll say tower capital Tj has a height lowercase tj. Which is the sum of the heights of blocks. Heights of blocks stacked on that tower. So, whenever I want to define the height of a tower, it's equal to the following. So Tj is going to be equal to the sum of, if I look at each block, Bi stacked on Tj. So I look at each of the blocks that are stacked on that tower, and I just simply add the heights of the blocks. That's what it says. That's what the height is of a tower. So for example, notice that the height of this tower, so imagine I have two towers. The two towers. I have one with height 1 because notice that the height of this block is 1. The height of each of these blocks is 1. So notice that the height of this tower is 2. It makes pretty good sense. I must stress that in our example here, the heights only are 1, but this works regardless if the heights were different. So just imagine you're stacking these blocks, and we're not really caring about them being oriented or anything. Just whenever you stack it, it has a height. So let's see where this goes. So let's see what happens. So let's define what the average height of a tower is. So the average height of a tower is the following. So it just simply should be the sum of all of the heights of the towers, right? Divided by how many towers there are. Right? That's just what the average would be. So it's just simply going through the collection, grabbing what the height is of that tower, summing all those up and dividing by how many there are. So there's P of them, right? So I sum over each of the towers. Divided by P. Now this is where it gets fun. The height, so in our collection, we had towers, right? Each has their height. So that means that there exists an equivalent collection for which consists of numbers, each containing in a position its height in that same spot. So we can just use the averaging principle. So the heights of the towers is a collection of numbers, right? So by the averaging principle, some tower has height at most mu, the average height of a tower, and some tower some tower has height at least mu. Now, I must stress that some tower, that means that also includes the tallest tower. Likewise, that right there, where we say the height is at most mu, that includes the shortest tower. So, now this is something really neat that I really want to point out to you. So let me grab my blocks. So when I compute the height of a tower, let me get my kitty friends out of the way. When I determine the height of a tower, it relies on me assigning blocks to towers to stack on top of each other. For example, this is one possible way I could have assigned the blocks to be on the tower, so it has height 3. But there could be towers that have no blocks on them. For example, there could be 3 towers, but this one has all the blocks on it. So, likewise, it also could be that it's potentially like this, with no blocks here. Likewise, it could be like this, where each one has their own block, and they all happen to be the same height, so they have all the same height. So, you might ask, Dan, is there something weird going on with this? Because when we walk through the averaging principle, the average was calculated like this. And it depends on the heights of the towers. So here's a neat kind of killer thing you can do with this. And I'm going to show you how you can do this. Now this is where the averaging principle becomes friendly with the way we defined everything here. So here's the wild fact you get from the averaging principle. So I'll put wild in quotation marks. So here's the wild fact. So we applied the averaging principle to the heights of the towers. Heights of the towers. But we actually don't need to know how the blocks are stacked in advance. So what I'm saying is you don't actually need to, like if somebody says to you, hey, look, this is how I'm going to stack my blocks. You don't have to say, by the averaging principle, well, I'm going to take the sum of all the heights of the towers, like 5, 3, and then there's one with 3. I don't actually need to have an assignment of the blocks to the towers to tell you that there is some tower with at least some height. I actually have all the information I need to calculate this information in advance. So that's the wild fact here. So let me show you why that is the case. So we don't actually need to know how the blocks are stacked in advance. This is because if I go over all the heights of the towers, divided by the number of towers, this is equal to the average, right? But the thing is, what does it mean to give me the height of a tower? Well, remember, the height of this tower is the sum of the heights of the blocks in it. This tower's height is the sum of the blocks in it. This tower that has no blocks in it, it has no blocks, but it's the sum of all the heights of the blocks, right? So if I'm adding them up anyways, summing up over all the heights of all the towers, well, each one of those was the sum of the heights of the blocks in the tower, and if all the blocks are already in some tower, this is actually equivalent to me writing this. It's actually the same as me writing over all of the blocks. So if I take all of the blocks, so these are my blocks. If I take the heights of all the blocks, these are actually equal to each other. So it means that you can actually determine that there is a tower that's going to have at least the height, at least some height, based on that calculation over there, which that is actually still the same thing. It's still the average height of a tower. But notice that I don't need to know anything about which tower the blocks were assigned to, because the way it works is that this is still a set of numbers, but the set of numbers now are just stored in the heights of the towers, but all of those can be decomposed into their blocks, right? Because I stacked those blocks on those towers, right? So I just take them all and pool them into one bucket, and now I have the heights of the blocks. And this is just simply because each one of these, by definition, is, as we stated previously, is just simply the heights of the blocks stacked on that tower. So if I have all those blocks, you get the right-hand side. So you actually don't need to know how the blocks are stacked in advance. You can actually calculate this without that information, well, in advance. So let me give you an example of what I mean by this. So it's going to be a little bit weird at first. If your brain isn't just churning this, just watch carefully. Okay, so suppose that I have, say, 3 towers. Well, this has 0, that's 0, this has height 3. So the average here would be the sum of the blocks. So I have 3 divided by how many bins I've got, or towers. So in this case, I have 3 over 3, which is 1. Now, let's do the same calculation again. The height of the towers in this case, 0, 1, 2, so still 3 divided by how many towers? 3. So 3 over 3, still 1. You can have them all like this. 1, 1, 1. Totals up to 3 for all the heights of the towers. Divided by 3, because there's 3 towers. Still get 1, right? So, do you see how this can actually be really clever for our usage if I want to know how tall at least the tallest tower could be? Because the tallest tower has to be either this element that is at least the average or bigger. And you can say the same thing about the shortest tower, too. So this actually is a very killer application. It's a very simple bound. I must admit, it's a very simple bound to observe. But this gives you an actual interesting caveat for how you could find out this information without ever having to say, hey, look, I have to actually examine what this looks like. I could just simply I could bring these all together and it doesn't make any difference. It's because of the way we define the height of a tower, right? So now let me throw this into the context of scheduling. So we're talking about stacking blocks. What we're actually talking about are scheduling machines with tasks. But yeah, notice that regardless of how I assign the blocks to the towers, notice that in any one case, it had to have been that at least one of the towers had how much for its height? 1, right? So just to kind of illustrate my point, I'm going to do this again now with 2 towers. The 2 towers. So imagine I have 2 towers, like this. The height of this one is 2, height of this is 1. The average would be, well, let's see, 2, 1 together. So that's 3 divided by 2, that's 1.5, right? So it's saying that there is a tower that has height at least 1.5. But look, there is one, it's right here, it's 2. So notice that regardless of how I assign them, you get the same calculation. 3, nothing. So 3 divided by 2, 1.5. Do you see how this is really nice? This is a nice property because it gives us information in advance about any possible assignment of the blocks to the towers, right? So, let me show you now where this could come in handy. So I'm going to show you a classic example from multiprocessor scheduling. So this is indeed a true computer science application. So it's a cute bound. It's a very cute bound. Some people would say it's obvious, but I would like to have some way for you to justify it for yourself that you're like, yeah, this is true. This is true. Because sometimes it's just thrown at you and like you just accept it. You aren't given a reason to believe it. So imagine. So we had our blocks, right? We had blocks that had heights. We had blocks that had heights. What I'm going to do is I want to reimagine the blocks instead as jobs or tasks. And each one is going to have a length pj. So we have blocks bi. Well, I'll call them bj with height hj. Now next, if we have a tower, TJ, actually we'll call it TI, just to keep it simple, with height TI. We're going to define that a machine MI has load that is just going to be the sum of all so it's going to be the assignment of a job onto that machine. And you should see that this is actually the same thing. It's the same thing. It's because this is just the sum of all the heights of the blocks. Right? So these are actually, when we talk about stacking blocks, we're actually talking about multiprocessor scheduling, where I can imagine I have my jobs and I have my machines. And keep in mind, these are very abstract concepts. They could just simply be literal. They could be a literal machine that takes in tasks. These could be people that are working on it in a team. This could, for example, be a set of like 3. Like if we had 2 stacks, these could be 2 workers. And you give them the blocks are tasks. And the heights they have are, in fact, the lengths of their jobs. So a very natural question is, so a natural goal in the right context is to schedule all the jobs to minimize the maximum load. So the maximum load is another way of me saying what we call the make span in scheduling theory. So this is the completion time of a machine that finishes last. Or equivalently, it is the completion time of a job that finishes last. So you want to minimize the maximum load. So if we can make it so that all of our machines finish as early as possible, as in the one that finishes last finishes as early as it can, that means that we can make the length of the schedule, which is what the make span is. You can think of this as the length of the schedule, as short as we can, right? This problem is actually quite hard compared to a lot of the cute problems that sometimes we talk about, like searching on an array. This problem, the best known exact algorithms take exponential time, but they're nice approximation algorithms. Many of them actually use a fact that actually comes from what we've actually just discussed here. Is actually that the following is, think about it. if these are actually just the same things, and I must stress that you can impose more constraints on how you can assign the blocks to the towers. Remember, the averaging principle just looks at a collection of numbers, right? In that case, it was the heights of the towers. In this case, it's just the loads of the machines, right? So regardless of how you decide to assign those jobs to the machines, just in the same way, we can talk about the average load of a machine. The average load of the machine equivalently can be defined like this. So I go over all the jobs. So imagine this is the set of all jobs. PJ. And remember that this right here is the same as me going across all of the machines and just simply adding up all of the jobs that are on all the machines that are currently scheduled. So keep in mind, this could be just the jobs that are presently scheduled as well. So I must stress this is a rather strong concept. So if I know this, remember the averaging principle would tell me that the maximal load of a machine is the make span. And we could use our previous reasoning that we had over here. It says that for any schedule, and this is any schedule. This is including a schedule with minimum make span. It has to be, by the same reasoning that we talked about with stacking our blocks, that if we sum up, so we get the sum of all of these, so the total sum of all the processing times of the jobs, or sum of the job lengths, and we get the this actually is the average load of the machines equivalently. This has to be less than or equal to the load of some machine, right? That's what the averaging principle would say, because you can imagine you have a collection of numbers. So you imagine you have m of these. So you have m numbers, each with the present load. So what the load is at this time. So the averaging principle would tell you that some machine here has load that is at least the average, and that load is most certainly going to be at least the maximal load, the make span, which you can define like this. And keep in mind, this is true for any schedule. So what happens is if you ever wanted to get a lower bound on the optimal make span, the average load in this setting, in this very specific setting, will be sufficient as a lower bound on the optimal make span. And this lower bound is very often used in scheduling theory for problems such as scheduling tasks on identical parallel machines, and of course, load balancing. So any questions? Any questions at all? Any questions at all? So I went a little bit faster with this one here. I have more details in the notes, if you're wondering kind of like the step-by-step kind of process. I'm hoping you've seen this connection between these two. As you can imagine, you have agents that you schedule tasks with. You want to finish all the tasks as early as possible. But this lower bound is a one that's that you could prove very easily using the averaging principle. It actually just falls right out of the averaging principle. Because if you just look at the loads of the machines, at least one of them has to be more or equal to the average load. And the average load is just simply the sum of all of the loads divided by how many machines there are. Oh, poop. I made a tiny typo. It's supposed to be M here, not N. Let me quickly fix that. So funny thing. This should actually be M because we have M machines. Actually, let's think about this. Did I ever define N? Nah, I think no, this is even worse. I didn't even define what N was. It's M. It's M, like this, because where M is the number of machines. But keep in mind that since I didn't define what N is, we're okay here. I just need to make sure I make a remark about how you need to, that N in our example here is the number of machines. However, in scheduling theory, M is normally used for number of machines. Somebody remind me of this fact. Yes, it's a very silly typo in my notes. I have to make sure that is accounted for. But yeah, so I thought I would show you that the averaging principle can be used to derive lower bounds. But I'm going to show you one last result for the day. And it's going to be a graph theory one. And it's going to be using mathematical induction, so prepare yourself. Okay, just gonna drink a little bit of water here. Okay. Okay, so let me just get our last thing we're going to see. And we're going to see an application of the averaging principle for proving a claim. Because previously, so I showed you how you can derive a lower bound using the averaging principle, which is really nice. That's something that you can use the averaging principle for. But I want to show you how you can use it in a setting quite similar to the one that we've talked about with the pigeonhole. So let's do this. I'm just going to try finding a marker that's a little bit more handy for us. Okay, let's go with this one. Okay, so previously we've seen how we can use the pigeonhole principle for proving claims, including those in graph theory. I thought I would show you an example of using the averaging principle to prove a graph theoretic claim. Now, as a reminder, the averaging principle is simply that if I take a collection of n numbers, the averaging principle states that there exists a number that is at least the average of the collection, and there exists an element that is at most the average in the collection. So we're going to prove a really basic property of graphs. So for any undirected graph. Oh, I don't like this marker. Let's switch to another one. I got a bunch of markers here. Just the question is which one? Which one? For any undirected graph, G is equal to VE with n vertices. With n vertices and m edges. If the number of edges is strictly less than n minus 1, then the graph G is disconnected. So that's a fun remark. If you have, say, exactly n minus 1 edges and your graph is connected, it's a tree. So we're going to give characterization when we have too few edges to end up with a graph that forms, say, something like a tree or a forest, or more. So we're going to do this by proving this claim using mathematical induction. So let us perform induction on n, the number of vertices. So we're going to denote a statement. So we're going to let d of n denote the statement the following statement. For any graph G on n vertices, if the number of edges is less than n minus 1, then G is disconnected. So just as a reminder, disconnected simply means that there exists at least two vertices such that there does not exist a path or a sequence of adjacent vertices to reach that other vertex. So just as a quick example, this is the disconnected graph because no vertex these vertices can't, none of them can reach that one. It's not reachable because there does not exist a sequence of adjacent vertices that I could, or path that I can walk from here to there. So, as this is an induction proof, we're going to start off with our base steps. So here I'm going to do a couple. So we're going to start with n is equal to 1. Now this is one of those weird cases where the statement becomes vacuously true because the statement doesn't even just sit, the condition can't even be applied when n is equal to 1. If n is equal to 1, the statement is what we call vacuously true. Vacuously true as the number of edges is never less than 1 minus 1, which equals 0, right? The number of edges have to be negative. That doesn't make any sense, right? So just to be clear why I'm saying that, is notice that the statement says if m is less than n minus 1, then this. Notice that, while true, if we have n is equal to 1, then 1 minus 1 is 0. You can't have a graph with a negative number of edges, so that condition, our condition is never satisfied. So this means this is false. This becomes vacuous, like it doesn't matter. It's still the conditional statement. It does, in logic we would say this is vacuously true. So it's just like it doesn't even apply, right? In fact, if you wanted to really convince yourself that this is still true, just here. Look, there's a graph with one vertex. It has no edges. It is in fact, but notice here, so that graph there is connected. However, it doesn't satisfy, it can't satisfy this, right? There are no such thing as negative edges. It can't satisfy the condition, the antecedent, as some people would say. It's one of these weird technical steps. That's why sometimes when people give you this proof or claim, they will just presume that there's at least two vertices. So let's do another base step just to play it safe. Keep in mind, you can do as many as you like, but we just need enough to make the jump. I would like to have it so that there's at least two vertices, other vertices that are present in the graph. So I'm going to go up a couple steps. If n is equal to 2, then d of 2 considers graphs on two vertices. Vertices with less than 2 minus 1 equals 1 edges. A graph with no edges consists of isolated vertices. Those are vertices that you just can't reach. They're just sort of sitting out here. In fact, the graph that I'm talking about would look like this. Just has two vertices like this, no edge. No edges. Consists of isolated vertices. Hence is disconnected. Hence is disconnected. Okay. That proves D of 2. So now we got our base steps in play. Now we're going to do the induction step. Now this is where we're going to get a little bit interesting because I'm going to pull out a couple of useful tools. One is going to be the averaging principle. Another is going to actually be the handshaking lemma, which we've previously proven using double counting. So let's do the induction step. So remember, this is just saying that if D of k, then D of k plus 1 follows. So we're going to fix some k greater or equal to 2. And we're going to now assume what we're going to call our induction hypothesis or inductive hypothesis. It's going to look like this. As I totally clobber myself. So for any graph G on k vertices, if the number of edges is less than k minus 1, then G is connected. So that's what D of k is. We're going to assume this holds. So this is our induction hypothesis or inductive hypothesis. Now we're going to show that D of k plus 1 holds, or follows. Actually, it follows. We wish to show that D of k plus 1 follows, which is the following. So it's everything I just wrote up there, where we replace everything with k, that was k with k plus 1. So we have to be careful with this. It's very easy to accidentally be sloppy here. So for any graph on k plus 1 vertices, if the number of edges is less than, okay, so in there it's k minus 1, but remember now we're 1 higher, so now it's going to be k minus 1 plus 1, which is just k. Less than k, then G is disconnected. So we want to show that D of k follow. If D of k, then D of k plus 1 follows. So now we have the setup for the induction step. Now, we're going to use a fact so that we can express something quite nice. Namely, we're going to use the handshaking lemma to help us express the average degree of a vertex. And you're going to see how we're going to use this. This is really actually quite clever. So now that we have a graph with k plus 1 vertices, so we're going to consider any graph g is equal to VE as in d of k plus 1. We're going to presume it's satisfying. It looks like this. It's going to have k plus 1 vertices and it has less than k edges. So by the handshaking lemma, which we've previously proven, by the handshaking lemma, we actually get a nice bound. But just as clarity, the handshaking lemma says this, that the sum of the degrees of the vertices in the graph is equal to exactly twice the number of edges. That's what our version of the handshaking lemma states. So now that we have this, let's proceed. Then, the average degree of a vertex is as follows. So you would agree with me that I just simply take the sum of all the degrees of all the vertices, and you divide by how many vertices there are, right? So that's just how many vertices I have. The handshaking lemma says that this is 2 times the number of edges. I'm just going to keep V like this. But now I have a nice bound here, because remember, the number of vertices and the number of edges, I know these things. So I know that the number of edges is less than k, right? And I also know the number of vertices. It is k plus 1. So I can say that this is less than 2k over k plus 1, right? Because there's k plus 1 vertices in the graph, and there's less than k edges in the graph. So that means that only that will get bigger, right? Because this is exactly the same quantity here, but this is bigger than that. But now look at this. K over k plus 1, is that less than 1, equal to 1, or greater than 1? Which one is it? It's only one of them. One of these 3 that are possible here. Well, think of it. So imagine you had 1. 1 over 1 plus 1, that's 1/2. 2. 2 over 2 plus 3, it's 2/3, right? Can you see a way I could get that to be greater than 1 or equal to 1? No, because the quantities there, it's k, it's something over something that's slightly bigger than it. As a fraction, that's always going to be less than 1 in our case. So that is going to now just be whatever. So I could just say that's less than 1. So this has to be less, this whole expression is less than 2. Now this is where it gets fun. Now I have a bound on the average degree. Spooky's a little excited. So let's think about this now. Spooky, calm down. We're trying to talk about the averaging principle. I know you're excited. We're about to make a very interesting conclusion based on this. Okay. So, now that we know that the average degree is at most 2, what does the averaging principle tell us now? By the averaging principle, Well, let's just see. Let's see. So it says it's at most 2. Like the average degree is at most 2. So does that mean the average degree can be 2 itself? No, it's always less than that. So that means the average has to take on the form of either 0 or 1, right? So by the averaging principle, there exists a vertex W that has degree 0 or 1, right? Those are the only possibilities, right? At least by using the averaging principle, right? Because it says that there exists an element that is at most or at least the average, right? Well, now we have a bound on how big that's going to be. This average can't go too wild. It's at most 2. So W has to have degree either 0 or 1. So the averaging principle tells you that there's going to be, so if I list out all of the vertices by their degrees, remember the average degree is calculated from that. That means there's going to exist one vertex that has at least or at most the average degree, and we know that how big the average degree can be. So this exhausts all possibilities for such a vertex by the averaging principle. Is that clear, everybody? So, because the averaging principle tells you that there exists such a thing. That's the key way we're using it. So we're going to have 2 possibilities. W is going to have degree 0, and then we're going to consider the case when the degree is 1 for W. So the first case is when the degree of W is equal to 0. This is the easy case. It's so easy that I could just whip together a very trivial argument here. Since W has no adjacent vertices, well, remember, a vertex with a degree 0 is isolated, right? And there are other vertices in the graph, right? That's why I made sure that there was more vertices. So that means that this is disconnected. Since W has no adjacent vertices, and vertices, and there are more vertices than just W, G is disconnected. That's an easy case. G is disconnected in this case. So in this case, just to be clear, you have W just sitting out here. Then there's other vertices that might be doing all sorts of other stuff. But the point is that this guy is sitting out over here, can't be reached by anybody else. So now we're going to be using our induction step to our full potential here in the second case. So we're going to consider when the degree of W is equal to 1. So we're going to let X be the vertex adjacent to W. Now remember, in this setup, the way it works is that I'm going to have W, it has degree 1, so it's going to look something like this. And then there could be other stuff that's happening. So W is just sort of hanging off of X, okay? By this one edge. So we're going to let G prime be the graph where both W and the edge WX, so the endpoints are W and X, are deleted. Now I want to remind you, this graph, the one I've just doodled over here, it has k plus 1 vertices, and it has less than how many edges? How many does it have? It has less than k, right? So when I delete this and delete this, notice that the number of edges and number of vertices goes down by 1. Interesting. Interesting. Then the number of vertices in G prime is k plus 1 minus 1, because we deleted w, which equals k, and the number of edges in G prime is less than k minus 1, because remember, originally it had less than k edges. Now, because I removed an edge, now it's less than k minus 1, right? so now you're staring at this, and you're like, okay, what's going on here? Now, this is where the fun of mathematical induction comes up. Okay. What did we say before? The graph, the new graph, G prime, it has k vertices and less than k minus 1 edges. What do we know about that, presuming that we all previously proven it? We know we've assumed d of k holds, right? But what's d of k? It says that there is a graph with k vertices and less than k minus 1 edges. And that graph has to be disconnected, right? So that's the induction hypothesis. Let's use that. G prime is a graph with k vertices and less than k minus 1 edges. So by the induction hypothesis, G prime is disconnected. So now we know G prime. When I took away these things, this has to be disconnected. So now we just have to reintroduce back in that edge and W. Vertex W is only adjacent to X in G. Therefore, G prime, and as a result, G remains disconnected when W and incident edge WX are introduced to G prime. Thus, this completes, since now I've accounted for both cases, thus completes the induction step. Now that we have the base steps sorted out, we got the induction step, now we can apply the principle of mathematical induction and we're done. Therefore, by the principle of mathematical induction, D of n is true for all n greater or equal to 1. And that completes the proof. There we go. So now we know that if you have too few edges in your graph, the graph is going to be disconnected. Remember, the big idea that we had here was that we combined the handshaking lemma so we took the handshaking lemma, we used that to help us formulate a bound for the average degree of a vertex. Then we've seen that the average degree of a vertex, in this case, it can be too big. It can't be too big. So that means that when we did that, we said, hey, look, the average, it can't vary too much, but there has to exist a vertex that is at least the average or at most the average. But it only could take on one of these values, right? So that means that we have a vertex that is going to take on potentially one of these 2 degrees. And we exhausted those cases in the induction step, and then we applied the principle of mathematical induction. So, being said, we've seen a nice application for how we could use the averaging principle to exhaust cases for the average degree. Sorry, not the average, for invoking the averaging principle to say some vertex has to have some degree that exists within either at least or at most the average. And we exhausted all possibilities for what the degree of that vertex can be. Because we know that there's some vertex with degree at least or at most that one. So, but we showed that it wasn't very big. So anyways, that being said, hopefully you found this averaging principle example helpful. So that way you could see, just like with the pigeonhole principle, how you can use it to help as a connecting step in your proof. But remember the conditions of the claim. The averaging principle is a generalization that applies for a collection of n real numbers, for example. And it's a really powerful statement for deriving lower bounds. And like in these cases, it's helpful for figuring out, hey, look, it'll tell you some information about the existence of, in our case, like a vertex or some object that has to be at most or at least the average. So honestly, let me just. So anyways, are there any questions? Any questions at all? Any questions? Don't be shy. Well, it doesn't seem like there's any questions. We got some fun things in the chat. But that being said, we're going to stop right here, I think. I think that we've hit everything we wanted to hit here. We had Miss Kitty hang out. We stacked some blocks. We had cats in boxes. We had cats jumping on me. We got cats, we got cats attacking my hands. We had all sorts of fun here. So if you enjoyed this content and you want access to these notes, consider supporting on Patreon at patreon.com/pagewizard. The notes for this will be available this evening. I just have to patch up a couple small little details. Like we mentioned, there was a small little typo for the number of machines. But other than that, of course, if you like this, make sure you like, follow, subscribe, tell your friends to come on out. We have ourselves a great time, and hope you enjoyed us going through all these fun little counting principles. I always enjoy doing this. Hope you found some of these techniques rather helpful. So that being said, I want to say thank you so much for coming on out, and have yourself a beautiful day. Later this week, I'll be playing some more Pokemon Scarlet, so you can check that out. I thought this December is a rather fun one for thinking about collecting and packing things. I thought this would follow in theme with that. And I had somebody asking me to cover Pigeonhole. So, that's it. I'll say thank you very much, and have yourself a beautiful day. I'll see you later.